Throughout history, humankind has struggled to understand the fundamental workings of the material world. We've endeavoured to discover the rules and patterns that determine the qualities of the objects that surround us, and their complex relationship to us and each other. Over thousands of years, societies all over the world have found that one discipline above all others yields certain knowledge about the underlying realities of the physical world. That discipline is mathematics. I'm Marcus de Sotoy, and I'm a mathematician. I see myself as a pattern searcher, hunting down the hidden structures that lie behind the apparent chaos and complexity of the world around us. In my search for pattern and order, I draw upon the work of the great mathematicians who've gone before me. People belonging to cultures across the globe, whose innovations created the language the universe is written in. I want to take you on a journey through time and space and track the growth of mathematics, from its awakening to the sophisticated subject we know today. Using computer-generated imagery, we'll explore the trailblazing discoveries that allowed the earliest civilizations to understand the world mathematically. This is the story of maths. Our world is made up of patterns and sequences. They're all around us. Day becomes night. Animals travel across the earth in ever-changing formations. Landscapes are constantly altering. One of the reasons mathematics began was because we needed to find a way of making sense of these natural patterns. The most basic concepts of maths, space and quantity, are hardwired into our brains. Even animals have a sense of distance and number, assessing when their pack is outnumbered and whether to fight or fly, calculating whether their prey is within striking distance. Understanding maths is the difference between life and death.
But it was man who took these basic concepts and started to build upon these foundations. At some point, humans started to spot patterns, to make connections, to count, and to order the world around them. And with this, a whole new mathematical universe began to emerge.
This is the River Nile. It's been the lifeline of Egypt for millennia. I've come here because it's where some of the first signs of mathematics as we know it today emerged. People abandoned nomadic life and began settling here as early as 6000 BC. The conditions were perfect for farming.
The most important event for Egyptian agriculture each year was the flooding of the Nile. So this was used as a marker to start each new year. Egyptians did record what was going on over periods of time. So in order to establish a calendar like this, you need to count how many days, for example, happened in between lunar phases, or how many days happened in between two floodings of the Nile.
Recording the patterns of the seasons was essential not only to their management of the land, but also their religion. The ancient Egyptians who settled on the Nile banks believed it was the river god Hapi who flooded the river each year. And in return for the life-giving water, the citizens offered a portion of the yield as a thanksgiving. As settlements grew larger, it became necessary to find ways to administer them. Areas of land needed to be calculated, crop yields predicted, taxes charged and collated. In short, people needed to count and measure. The Egyptians used their bodies to measure the world, and it's how their units of measurement evolved. A palm was the width of a hand. A cubit, an arm length from elbow to fingertips. Land cubits, strips of land measuring a cubit by 100, were used by the pharaoh's surveyors to calculate areas.
There's a very strong link between bureaucracy and the development of mathematics in ancient Egypt. And we can see this link right from the beginning, from the invention of the number system, throughout Egyptian history, really. For the Old Kingdom, the only evidence we have are metrological systems, that is, measurements for areas, for length. This points to a bureaucratic need to develop such things.
It was vital to know the area of a farmer's land so he could be taxed accordingly. Or if the Nile robbed him of part of his land, so he could request a rebate. It meant that the pharaoh's surveyors were often calculating the area of irregular parcels of land. And it was the need to solve such practical problems that made them the earliest mathematical innovators. The Egyptians needed some way to record the results of their calculations. Amongst all the hieroglyphs that cover the tourist souvenirs scattered around the city of Cairo, I was on the hunt for those that recorded some of the first numbers in history. They were difficult to track down. But I did find them in the end. The Egyptians were using a decimal system, motivated by the 10 fingers on our hands. The sign for 1 was a stroke, 10 a heel bone, 100 a coil of rope, and 1,000 a lotus plant.
Yeah, how much is this t-shirt? 25. Yes. So that would be 2 knee bones and 5 strokes. Yes. So you're not going to charge me anything up here?
Here, 1 million.
1 million?
Oh my God.
No.
Is this 1 million?
1 million. Yeah, that's pretty big.
The hieroglyphs are beautiful, but the Egyptian number system was fundamentally flawed. They had no concept of a place value. So 1 stroke could only represent 1 unit, not 100 or 1,000. Although you can write 1,000,000 with just 1 character, rather than the 7 that we use, if you want to write 1,000,000 minus 1, then the poor old Egyptian scribe has got to write 9 strokes, 9 heel bones, 9 coils of rope, and so on, a total of 54 characters. Despite the drawback of this number system, the Egyptians were brilliant problem solvers.
We know this because of the few records that have survived. The Egyptian scribes used sheets of papyrus to record their mathematical discoveries. This delicate material made from reeds decayed over time, and many secrets perished with it. But there's one revealing document that has survived.
The Rhind mathematical papyrus is the most important document we have today for Egyptian mathematics. We get a good overview of what types of problems the Egyptians would have dealt with in their mathematics. We also get explicitly stated how multiplications and divisions were carried out.
The papyri show how to multiply 2 large numbers together. But to illustrate the method, let's take 2 smaller numbers. Let's do 3 times 6. The scribe would take the first number 3 and put it in one column. In the second column, he would place the number 1. Then he would double the numbers in each column. So 3 becomes 6, and 6 would become 12. And then in the second column, 1 would become 2, and 2 becomes 4. Now here's the really clever bit. The scribe wants to multiply 3 by 6. So he takes the powers of 2 in the second column, which add up to 6. So that's 2 plus 4. Then he moves back to the first column and just takes those rows corresponding to the 2 and the 4. So that's 6 and the 12. He adds those together to get the answer of 18. But for me, the most striking thing about this method is that the scribe has effectively written that second number in binary. 6 is 1 lot of 4, 1 lot of 2, and no units, which is 1, 1, 0. the Egyptian symbols that were used in ancient Egypt.
The Rhine Papyrus was recorded by a scribe called Ahmes around 1650 BC, and its problems are concerned with finding solutions to everyday situations. Several of the problems mention bread and beer, which isn't surprising as Egyptian workers were paid in food and drink. One is concerned with how to divide 9 loaves equally between 10 people without a fight breaking out.
I've got 9 loaves of bread here. I'm going to take 5 of them and cut them into halves.
Of course, 9 people could shave a 10th off their loaf and give the pile of crumbs to the 10th person. But the Egyptians developed a far more elegant solution.
Take the next 4 and divide those into thirds. But 2 of the thirds I'm now going to cut into fifths, so each piece will be 1/15. Each person then gets 1/2 and 1/3 and 1/15. It's through such seemingly practical problems that we start to see a more abstract mathematics developing. Suddenly new numbers are on the scene, fractions, and it isn't too long before the Egyptians are exploring the mathematics of these numbers.
Fractions are clearly of practical importance to anyone dividing quantities for trade in the market. To log these transactions, the Egyptians developed notation which recorded these new numbers. One of the earliest representations of these fractions came from a hieroglyph which had great mystical significance. It's called the Eye of Horus. Horus was an Old Kingdom god, depicted as half man, half falcon.
According to legend, Horus's father was killed by his other son, Seth. Horus was determined to avenge the murder. During one particularly fierce battle, Seth ripped out Horus's eye, tore it up and scattered it over Egypt. But the gods were looking favourably on Horus. They gathered up the scattered pieces and reassembled the eye.
Each part of the eye represented a different fraction, each one half the fraction before. Although the original eye represented a whole unit, the reassembled eye is 1/64 short. Although the Egyptians stopped at 1/64, implicit in this picture is the possibility of adding more fractions, halving them each time, the sum getting closer and closer to 1, but never quite reaching it. This is the first hint of something called a geometric series, and it appears at a number of points in the Rhine Papyrus. But the concept of infinite series would remain hidden until the mathematicians of Asia discovered it centuries later. Having worked out a system of numbers, including these new fractions, it was time for the Egyptians to apply their knowledge to understanding shapes that they encountered day to day. These shapes were rarely regular squares or rectangles, and in the Rhine Papyrus we find the area of a more organic form, the circle.
What is astounding in the calculation of the area of a circle is its exactness, really. How they would have found their method is open to speculation because the texts we have do not show us the methods how they were found.
This calculation is particularly striking because it depends on seeing how the shape of the circle can be approximated by shapes that the Egyptians already understood. The Rhine Papyrus states that a circular field with a diameter of 9 units is close in area to a square with sides of 8. But how would this relationship have been discovered? My favourite theory sees the answer in the ancient game of Mancala. Mancala boards were found carved on the roofs of temples. Each player starts with an equal number of stones, and the object of the game is to move them around the board, capturing your opponent's counters on the way.
As the players sat around waiting to make their next move, perhaps one of them realised that sometimes the balls fill the circular holes of the Mancala board in a rather nice way. He might have gone on to experiment with trying to make larger circles.
Perhaps he noticed that 64 stones, the square of 8, can be used to make a circle with diameter 9 stones. By rearranging the stones, the circle has been approximated by a square. And because the area of a circle is pi times the radius squared, the Egyptian calculation gives us the first accurate value for pi.
The area of the circle is 64. Divide this by the radius squared, in this case 4.5 squared, and you get a value for pi. So 64 divided by 4.5 squared is 3.16, just a little under 2/100ths away from its true value. But the really brilliant thing is the Egyptians are using these smaller shapes to capture the larger shape.
But there's one imposing and majestic symbol of Egyptian mathematics we haven't attempted to unravel yet: the pyramid. I've seen so many pictures that I couldn't believe I'd be impressed by them. But meeting them face to face, you understand why they're called one of the 7 wonders of the ancient world. They're simply breathtaking. And how much more impressive they must have been in their day, when the sides were as smooth as glass, reflecting the desert sun.
To me, it looks like there might be mirror pyramids hiding underneath the desert, which will complete these shapes to make perfectly symmetrical octahedrons. Sometimes, in the shimmer of the desert heat, you can almost see these shapes.
It's the hint of symmetry hidden inside these shapes that makes them so impressive for a mathematician. The pyramids are just a little short to create these perfect shapes. But some have suggested that another important mathematical concept might be hidden inside the proportions of the Great Pyramid: the golden ratio. 2 lengths are in the golden ratio if the relationship of the longest to the shortest is the same as the sum of the 2 to the longest side. Such a ratio has been associated with the perfect proportions one finds all over the natural world, as well as in the work of artists, architects and designers for millennia. Whether the architects of the pyramids were conscious of this important mathematical idea, or were instinctively drawn to it because of its satisfying aesthetic properties, we'll never know. For me, the most impressive thing about the pyramids is the mathematical brilliance that went into making them, including the first inkling of one of the great theorems of the ancient world, Pythagoras' theorem.
In order to get perfect right-angled corners on their buildings and pyramids, the Egyptians would have used a rope with knots tied in it. At some point, the Egyptians realised that if they took a triangle with sides marked with 3 knots, 4 knots and 5 knots, it guaranteed them a perfect right angle. This is because 3 squared plus 4 squared is equal to 5 squared. So we've got a perfect Pythagorean triangle. In fact, any triangle whose sides satisfy this relationship will give me a 90-degree angle. But I'm pretty sure that the Egyptians hadn't got this sweeping generalization of their 3-4-5 triangle.
We would not expect to find a general proof because this is not the style of Egyptian mathematics. Every problem was solved using concrete numbers, and then if a verification would be carried out at the end, it would use the result and these concrete given numbers. There's no general proof within the Egyptian mathematical texts.
It would be some 2,000 years before the Greeks and Pythagoras would prove that all right-angled triangles shared certain properties. This wasn't the only mathematical idea that the Egyptians would anticipate. In a 4,000-year-old document called the Moscow Papyrus, we find a formula for the volume of a pyramid with its peak sliced off, which shows the first hint of calculus at work.
For a culture like Egypt that is famous for its pyramids,
such that the highest point sits directly over one corner. 3 of these can be put together to make a rectangular box. So the volume of the skewed pyramid is 1/3 the volume of the box. That is, the height times the length times the width divided by 3.
Now comes an argument which shows the very first hints of the calculus at work, thousands of years before Gottfried Leibniz and Isaac Newton would come up with the theory.
Suppose you could cut the pyramid into slices. You could then slide the layers across to make the more symmetrical pyramid you see in Giza. However, the volume of the pyramid has not changed, despite the rearrangement of the layers. So the same formula works. The Egyptians were amazing innovators, and their ability to generate new mathematics was staggering. For me, they revealed the power of geometry and numbers, and made the first moves towards some of the exciting mathematical discoveries to come. But there was another civilization that had mathematics to rival that of Egypt, and we know much more about their achievements. This is Damascus, over 5,000 years old and still vibrant and bustling today. It used to be the most important point on the trade routes linking old Mesopotamia with Egypt. The Babylonians controlled much of modern-day Iraq, Iran and Syria from 1800 BC. In order to expand and run their empire, they became masters of managing and manipulating numbers.
We have law codes, for instance, that tell us about the way society is ordered. Now, the people we know most about are the scribes, the professionally literate and numerate people who kept the records for the wealthy families and for the temples and palaces.
Scribe schools existed from around 2500 BC. Aspiring scribes were sent there as children and learned how to read, write, and work with numbers. Scribe records were kept on clay tablets, which allowed the Babylonians to manage and advance their empire. However, many of the tablets we have today aren't official documents, but children's exercises. It's these unlikely relics that give us a rare insight into how the Babylonians approached mathematics.
So this is a geometrical textbook from about the 18th century BC, and I hope you can see that there are lots of pictures on it, and underneath each picture is a text that sets a problem about the picture. So, for instance, this one here says, I drew a square 60 units long, and inside it I drew 4 circles. What are their areas? And this little tablet here was written 1,000 years at least later than the tablet here, but it has a very interesting relationship to it. It also has 4 circles in a square, roughly drawn, but this isn't a textbook, it's a school exercise, so that the adult scribe who's teaching the student is being given this as an example of completed homework or something like that.
Like the Egyptians, the Babylonians appeared interested in solving practical problems to do with measuring and weighing. The Babylonian solutions to these problems are written like mathematical recipes. A scribe would simply follow and record a set of instructions to get a result. Here's an example of a kind of problem they'd solve.
Now I've got a bundle of cinnamon sticks here, but I'm not going to weigh them. Instead, I'm going to take 4 times their weight and add them to the scales. Now I'm going to add 20 gin. Gin was the ancient Babylonian measure of weight. I'm going to take half of everything here and add it again. So that's 2 bundles and 10 gin. Now everything on this side is equal to 1 manna. 1 manna was 60 gin. And here we have one of the first mathematical equations in history. Everything on this side is equal to 1 manna. But how much does the bundle of cinnamon sticks weigh? Without any algebraic language, they were able to manipulate the quantities to be able to prove that the cinnamon sticks weighed 5 gin. In my mind, it's this kind of problem which gives mathematics a bit of a bad name. You can blame those ancient Babylonians for all those tortuous problems you had at school. But the ancient Babylonian scribes excelled at this kind of problem.
Intriguingly, they weren't using powers of 10 like the Egyptians. They were using powers of 60.
The Babylonians invented their number system, like the Egyptians, by using their fingers. But instead of counting through the 10 fingers on their hand, Babylonians found a much more intriguing way to count body parts. They used the 12 knuckles on one hand and the 5 fingers on the other to be able to count 12 times 5, i.e. 60 different numbers. So for example, this number would have been 2 lots of 12, 24, and then 1, 2, 3, 4, 5 to make 29.
But the number 60 had another powerful property. It can be perfectly divided in a multitude of ways. Here are 60 beans. I can arrange them in 2 rows of 30, 3 rows of 20, 4 rows of 15, 5 rows of 12, or 6 rows of 10. The divisibility of 60 makes it a perfect base in which to do arithmetic. The base 60 system was so successful, we still use elements of it today. Every time we want to tell the time, we recognise units of 60, 60 seconds in a minute, 60 minutes in an hour. But the most important feature of the Babylonians' number system was that it recognised place value. Just as our decimal numbers count how many lots of tens, hundreds and thousands you're recording, the position of each Babylonian number records the power of 60 you're counting.
Instead of inventing new symbols for bigger and bigger numbers, they would write 111, so this number would be 3,661. The catalyst for this discovery was the Babylonians' desire to chart the course of the night sky.
The Babylonians' calendar was based on the cycles of the moon, and so they needed a way of recording astronomically large numbers. Month by month, year by year, these cycles were recorded. From about 800 BC, there were complete lists of lunar eclipses.
The Babylonian system of measurement was quite sophisticated at that time. They had a system of angular measurement, 360 degrees in a full circle. Each degree was divided into 60 minutes. A minute was further divided into 60 seconds. So they had a regular system for measurement, and it was in perfect harmony with their number system. So it was well suited not only for observation, but also for calculation.
But in order to calculate and cope with these large numbers, the Babylonians needed to invent a new symbol. And in so doing, they prepared the ground for one of the great breakthroughs in the history of mathematics: 0.
In the early days, the Babylonians, in order to mark an empty place in the middle of a number, would simply leave a blank space. So they needed a way of representing nothing in the middle of a number. So they used a sign as a sort of breathing mark or a punctuation mark, and it comes to mean 0 in the middle of a number.
This was the first time 0 in any form had appeared in the mathematical universe. But it'd be over 1,000 years before this little placeholder would become a number in its own right. Having established such a sophisticated system of numbers, they harnessed it to tame the arid and inhospitable land that ran through Mesopotamia. Babylonian engineers and surveyors found ingenious ways of accessing water and channeling it to the crop fields. Yet again, they used mathematics to come up with solutions. The Orontes Valley in Syria is still an agricultural hub, and the old methods of irrigation are being exploited today just as they were thousands of years ago. Many of the problems in Babylonian mathematics are concerned with measuring land, and it's here we see for the first time the use of quadratic equations, one of the greatest legacies of Babylonian mathematics.
Quadratic equations involve things where the unknown quantity you're trying to identify is multiplied by itself. We call this squaring because it gives the area of a square. And it's in the context of calculating the area of land that these quadratic equations naturally arise.
Here's a typical problem. If a field has an area of 55 units, and one side is 6 units longer than the other, how long is the shorter side? The Babylonian solution was to reconfigure the field as a square. Cut 3 units off the end, and move this round. Now, there's a 3x3 piece missing, so let's add this in. The area of the field has increased by 9 units. This makes the new area 64, so the size of the square are 8 units. The problem solver knows that they've added 3 to this side, so the original length must be 5. It may not look like it, but this is one of the first quadratic equations in history.
In modern mathematics, I would use the symbolic language of algebra to solve this problem. But the amazing feat of the Babylonians is that they were using these geometric games to find the value, without any recourse to symbols or formulas. The Babylonians were enjoying problem solving for its own sake. They were falling in love with mathematics.
The Babylonians' fascination with numbers soon found a place in their leisure time too. They were avid game players. The Babylonians and their descendants have been playing a version of backgammon for over 5,000 years.
So the Babylonians played board games, from very posh board games in royal tombs to little bits of board games found in schools, to board games scratched on the entrances of palaces, so that the guardsmen must have played at times when they were bored. And they used dice to move their counters round. People who played games were using numbers in their leisure time to try and outwit their opponent, doing mental arithmetic very fast. And so they were calculating in their leisure time without even thinking about it as being mathematical hard work.
That's my chance.
I hadn't played backgammon for ages, but I reckon my maths would be good enough to give me a fighting chance.
Okay. So it's up to you.
So 6, and I need to move something, so...
But it wasn't as easy as I thought.
What the hell is that?
Yeah, this is...
1, this is 2. Now you're in trouble.
So I can't move anything, can I? I can't move these anyway.
You cannot move these. You can.
I've just got to... Oh, gosh.
Exactly. There you go.
You seem to be...
3 and 4. So.
Just like the ancient Babylonians, my opponents were masters of tactical mathematics.
Yeah. Put it there.
There you
All right,
go.
good game.
The Babylonians are recognized as one of the first cultures to use symmetrical mathematical shapes to make dice. But there is more heated debate about whether they might also have been the first to discover the secrets of another important shape, the right-angled triangle. We've already seen how the Egyptians used a 3-4-5 right-angled triangle. But what the Babylonians knew about this shape, and others like it, is much more sophisticated. This is the most famous and controversial ancient tablet we have. It's called Plimpton 322. Many mathematicians are convinced it shows the Babylonians could well have known the principle regarding right-angled triangles, that the square on the diagonal is the sum of the squares on the sides, and known it centuries before the Greeks claimed it.
This is a copy of the arguably most famous Babylonian tablet, which is Plimpton 322, and these numbers here reflect the width or height of a triangle, this being the diagonal. The other side would be over here, and the square of this column plus the square of the number in this column equals the square of the diagonal. They are arranged in an order of steadily decreasing angle on a very uniform basis, showing that somebody had a lot of understanding of how the numbers fit together.
Here were 15 perfect Pythagorean triangles, all of whose sides had whole number lengths. It's tempting to think that the Babylonians were the first custodians of Pythagoras' theorem, and it's a conclusion that generations of historians have been seduced by.
But there could be a much simpler explanation for the sets of three numbers which fulfill Pythagoras' theorem.
It's not a systematic explanation of Pythagorean triples. It's simply a mathematics teacher doing some quite complicated calculations, but in order to produce some very simple numbers in order to set his students problems about right-angled triangles. And in that sense, it's about Pythagorean triples, only incidentally.
The most valuable clues to what they understood could lie elsewhere. This small school exercise tablet is nearly 4,000 years old and reveals just what the Babylonians did know about right-angled triangles. It uses the principle of Pythagoras' theorem to find the value of an astounding new number.
Drawn along the diagonal is a really very good approximation to the square root of 2. And so that shows us that it was known and used in school environments. Now, why is this important? It's because the square root of 2 is what we now call an irrational number. That is, if we write it out in decimals or even in sexagesimal places, it doesn't end. The numbers go on forever after the decimal point.
The implications of this calculation are far-reaching. Firstly, it means the Babylonians knew something of Pythagoras' theorem 1,000 years before Pythagoras. Secondly, the fact that they can calculate this number to an accuracy of 4 decimal places shows an amazing arithmetic facility, as well as a passion for mathematical detail.
The Babylonians' mathematical dexterity was astounding, and for nearly 2,000 years they spearheaded intellectual progress in the ancient world. But when their imperial power began to wane, so did their intellectual vigour. By 330 BC, the Greeks had advanced their imperial reach into old Mesopotamia. This is Palmyra in central Syria, a once great city built by the Greeks. The mathematical expertise needed to build structures with such geometric perfection is impressive. Just like the Babylonians before them, the Greeks were passionate about mathematics.
The Greeks were clever colonists. They took the best from the civilizations they invaded to advance their own power and influence. But they were soon making contributions themselves. In my opinion, their greatest innovation was to do with a shift in the mind. What they initiated would influence humanity for centuries. They gave us the power of proof.
Somehow they decided that they had to have a deductive system for their mathematics. And the typical deductive system was to begin with certain axioms which you assume are true. It's as if you assume a certain theorem is true without proving it. And then using logical methods and very careful steps, from these axioms you prove theorems. And then from those theorems you prove more theorems. And it just snowballs that way.
Proof is what gives mathematics its strength. It's the power of proof, which means that the discoveries of the Greeks are as true today as they were 2,000 years ago. I needed to head west into the heart of the old Greek Empire to learn more. For me, Greek mathematics has always been heroic and romantic. I'm on my way to Samos, less than a mile from the Turkish coast. This place has become synonymous with the birth of Greek mathematics, and it's down to the legend of one man.
His name is Pythagoras. The legends that surround his life and work have contributed to the celebrity status he has gained over the last 2,000 years. He's credited, rightly or wrongly, with beginning the transformation from mathematics as a tool for accounting to the analytic subject we recognise today.
Pythagoras is a controversial figure. Because he left no mathematical writings, many have questioned whether he indeed solved any of the theorems attributed to him. He founded a school in Samos in the 6th century BC, but his teachings were considered suspect, and the Pythagoreans a bizarre sect.
There is good evidence that there were schools of Pythagoreans. They may have looked more like sects than what we associate with philosophical schools, because they didn't just share knowledge, they also shared a way of life. They may have been a communal living, and they all seem to have been involved in the politics of their cities. One feature that makes them unusual in the ancient world is that they included women.
But Pythagoras is synonymous with understanding something that eluded the Egyptians and the Babylonians, the properties of right-angled triangles. What's known as Pythagoras' theorem states that if you take any right-angled triangle, build squares on all the sides, then the area of the largest square is equal to the sum of the squares on the two smaller sides.
It's at this point for me that mathematics is born, and a gulf opens up between the other sciences. And the proof is as simple as it is devastating in its implications.
Place 4 copies of the right-angled triangle on top of this surface. The square that you now see has sides equal to the hypotenuse of the triangle. By sliding these triangles around, we see how we can break the area of the large square up into the sum of two smaller squares, whose sides are given by the two short sides of the triangle. In other words, the square on the hypotenuse is equal to the sum of the squares on the other sides. Pythagoras' theorem. It illustrates one of the characteristic themes of Greek mathematics, the appeal to beautiful arguments in geometry rather than a reliance on number.
Pythagoras may have fallen out of favour, and many of the discoveries accredited to him have been contested recently. But there's one mathematical theory that I'm loath to take away from him. It's to do with music and the discovery of the harmonic series.
The story goes that walking past a blacksmith's one day, Pythagoras heard anvils being struck and noticed how the notes being produced sounded in perfect harmony. He believed that there must be some rational explanation to make sense of why the notes sounded so appealing. The answer was mathematics. Experimenting with a stringed instrument, Pythagoras discovered that the intervals between harmonious musical notes were always represented as whole number ratios. And here's how he might have constructed his theory.
First, play a note on the open string. Next, take half the length. The note almost sounds the same as the first note. In fact, it's an octave higher, but the relationship is so strong we give these notes the same name. Now, take a third the length. We get another note which sounds harmonious next to the first two. But take a length of string which is not in a whole number ratio, and all we get is dissonance.
According to legend, Pythagoras was so excited by this discovery that he concluded the whole universe was built from numbers. But he and his followers were in for a rather unsettling challenge to their worldview. And it came about as a result of the theorem which bears Pythagoras' name. Legend has it, one of his followers, a mathematician called Hippasus, set out to find the length of the diagonal for a right-angled triangle with two sides measuring 1 unit. Pythagoras' theorem implied that the length of the diagonal was a number whose square was 2. The Pythagoreans assumed that the answer would be a fraction. But when Hippasus tried to express it in this way, no matter how he tried, he couldn't capture it. Eventually, he realized his mistake. It was the assumption that the value was a fraction at all which was wrong. The value of the square root of 2 was the number that the Babylonians etched into the Yale tablet. However, they didn't recognize the special character of this number, but Hippasus did. It was an irrational number.
The discovery of this new number, and others like it, is akin to an explorer discovering a new continent, or a naturalist finding a new species. But these irrational numbers didn't fit the Pythagorean worldview. Later Greek commentators tell the story of how Pythagoras swore his sect to secrecy, but Hippasus let slip the discovery and was promptly drowned for his attempts to broadcast their research.
But these mathematical discoveries could not be easily suppressed. Schools of philosophy and science started to flourish all over Greece, building on these foundations. The most famous of these was the Academy. Plato founded this school in Athens in 387 BC. Although we think of him today as a philosopher, he was one of mathematics' most important patrons. Plato was enraptured by the Pythagorean worldview and considered mathematics the bedrock of knowledge.
Some people would say that Plato is possibly the most influential figure for our perception of Greek mathematics. He argued that mathematics is an important form of knowledge and does have a connection with reality. So by knowing mathematics, we'll know more about reality.
In his dialogue Timaeus, Plato proposes the thesis that geometry is the key to unlocking the secrets of the universe, a view still held by scientists today. Indeed, the importance Plato attached to geometry is encapsulated in the sign that was mounted above the Academy. Let no one ignorant of geometry enter here.
Plato proposed that the universe could be crystallized into 5 regular symmetrical shapes. These shapes, which we now call the Platonic solids, were composed of regular polygons assembled to create 3-dimensional symmetrical objects. The tetrahedron represented fire. The icosahedron, made from 20 triangles, represented water. The stable cube was earth. The 8-faced octahedron was air. And the 5th Platonic solid, the dodecahedron, made out of 12 pentagons, was reserved for the shape which captured Plato's view of the universe. Plato's theory would have a seismic influence and continue to inspire mathematicians and astronomers for over 1,500 years. In addition to the breakthroughs made in the Academy, mathematical triumphs were also emerging from the edge of the Greek Empire, and owed as much to the mathematical heritage of the Egyptians as the Greeks. Alexandria became a hub of academic excellence under the rule of the Ptolemies in the 3rd century BC, and its famous library soon gained a reputation to rival Plato's Academy.
The kings of Alexandria were prepared to invest in the arts, in culture, in technology, mathematics, grammar, because patronage for cultural pursuits was one way of showing that you were a more prestigious ruler and had a better entitlement to greatness.
The old library and its precious contents were destroyed when the Muslims conquered Egypt in the 7th century. But its spirit is alive in a new building. Today, the library remains a place of discovery and scholarship.
Mathematicians and philosophers flocked to Alexandria, driven by their thirst for knowledge and the pursuit of excellence. The patrons of the library were the first professional scientists, individuals who were paid for their devotion to research. But of all those early pioneers, my hero is the enigmatic Greek mathematician Euclid.
We know very little about Euclid's life, but his greatest achievements were as a chronicler of mathematics. Around 300 BC, he wrote the most important textbook of all time, the Elements. In the Elements, we find the culmination of the mathematical revolution which had taken place in Greece. It's built on a series of mathematical assumptions called axioms. For example, a line can be drawn between any 2 points. From these are made and mathematical theorems established. The Elements contains formulas for calculating the volumes of cones and cylinders, proofs about geometric series, perfect numbers, and primes. The climax of the elements is a proof that there are only 5 Platonic solids. For me, this last theorem captures the power of mathematics. It's one thing to build 5 symmetrical solids, quite another to come up with a watertight, logical argument for why there can't be a 6th. The elements unfold like a wonderful logical mystery novel. But this is a story which transcends time. Scientific theories get knocked down from one generation to the next. But the theorems in the elements are as true today as they were 2,000 years ago.
When you stop and think about it, it's really amazing that it's the same theorems that we teach. We may teach them in a slightly different way, or we may organize them differently, but it's Euclidean geometry that is still valid, and even in higher mathematics. When you go to higher dimensional spaces, you're still using Euclidean geometry.
Alexandria must have been an inspiring place for the ancient scholars, and Euclid's fame would have attracted even more eager young intellectuals to the Egyptian port. One mathematician who particularly enjoyed the intellectual environment in Alexandria was Archimedes.
He would become a mathematical visionary.
The best Greek mathematicians, they were always pushing the limits, pushing the envelope. So Archimedes did what he could with polygons, with solids. He then moved on to centers of gravity, or he then moved on to the spiral. This instinct to try and mathematize everything is something that I see as a legacy.
One of Archimedes' specialities was weapons of mass destruction. They were used against the Romans when they invaded his home of Syracuse in 212 BC. He also designed mirrors which harnessed the power of the sun to set the Roman ships on fire. But to Archimedes, these endeavours were mere amusements in geometry. He had loftier ambitions.
Archimedes was enraptured by pure mathematics and believed in studying mathematics for its own sake, and not for the ignoble trade of engineering or the sordid quest for profit.
One of his finest investigations into pure mathematics was to produce formulas to calculate the areas of regular shapes.
Archimedes' method was to capture new shapes by using shapes he already understood. So, for example, to calculate the area of a circle, he would enclose it inside a triangle. And then by doubling the number of sides on the triangle, the enclosing shape would get closer and closer to the circle. Indeed, we sometimes call a circle a polygon with an infinite number of sides. But by estimating the area of the circle, Archimedes is in fact getting a value for pi, the most important number in mathematics.
However, it was calculating the volumes of solid objects where Archimedes excelled. He found a way to calculate the volume of a sphere by slicing it up and approximating each slice as a cylinder. He then added up the volumes of the slices to get an approximate value for the sphere. But his act of genius was to see what happens if you make the slices thinner and thinner. In the limit, the approximation becomes an exact calculation. But it was Archimedes' commitment to mathematics that will be his undoing.
Archimedes was contemplating a problem about circles traced in the sand when a Roman soldier accosted him. Archimedes was so engrossed in his problem that he insisted he'd be allowed to finish his theorem. But the Roman soldier was not interested in Archimedes' problem and killed him on the spot. Even in death, Archimedes' devotion to mathematics was unwavering.
By the middle of the 1st century BC, the Romans had tightened their grip on the old Greek Empire. They were less smitten with the beauty of mathematics and were more concerned with its practical applications. This pragmatic attitude signalled the beginning of the end for the great library of Alexandria. But one mathematician was determined to keep the legacy of the Greeks alive. Hypatia was exceptional, a female mathematician, and a pagan in the piously Christian Roman Empire.
Hypatia was very prestigious and very influential in her time. She was a teacher with a lot of students, a lot of followers. She was politically influential in Alexandria. So it's this combination of high knowledge and high prestige that may have made her a figure of hatred for the Christian mob.
One morning during Lent, Hypatia was dragged off her chariot by a zealous Christian mob and taken to a church. There she was tortured and brutally murdered. The dramatic circumstances of her life and death fascinated later generations. Sadly, her cult status eclipsed her mathematical achievements. She was in fact a brilliant teacher and theorist, and her death dealt a final blow to the Greek mathematical heritage of Alexandria. My travels have taken me on a fascinating journey to uncover the passion and innovation of the world's earliest mathematicians. It's the breakthroughs made by those early pioneers of Egypt, Babylon and Greece that are the foundations on which my subject is built today. But this is just the beginning of my mathematical odyssey. The next leg of my journey lies east in the depths of Asia, where mathematicians scaled even greater heights in pursuit of knowledge. With this new era came a new language of algebra and numbers, better suited to telling the next chapter in the story of maths. You can learn more about the story of maths with the Open University at From measuring time to understanding our position in the universe. From mapping the Earth to navigating the seas. From man's earliest inventions to today's advanced technologies, mathematics has been the pivot on which human life depends. The first steps of man's mathematical journey were taken by the ancient cultures of Egypt, Mesopotamia and Greece. Cultures which created the basic language of number and calculation. But when ancient Greece fell into decline, mathematical progress juddered to a halt. But that was in the West. In the East, mathematics would reach dynamic new heights. But in the West, much of this mathematical heritage has been conveniently forgotten or shaded from view. Due credit has not been given to the great mathematical breakthroughs that ultimately changed the world we live in. This is the untold story of the mathematics of the East that would transform the West and give birth to the modern world. The Great Wall of China stretches for thousands of miles. Nearly 2,000 years in the making, this vast defensive wall was begun in 220 BC to protect China's growing empire.
The Great Wall of China is an amazing feat of engineering, built over rough and high countryside. As soon as they started building, the ancient Chinese realized they had to make calculations about distances, angles of elevation, and amounts of material. So perhaps it isn't surprising that this inspired some very clever mathematics to help build Imperial China.
At the heart of ancient Chinese mathematics was an incredibly simple number system, which laid the foundations for the way we count in the West today. When a mathematician wanted to do a sum, he would use small bamboo rods. These rods were arranged to represent the numbers 1 to 9. They were then placed in columns, each column representing units, tens, hundreds, thousands, and so on. So the number 924 was represented by putting the symbol 4 in the units column, the symbol 2 in the tens column, and the symbol 9 in the hundreds column. 924.
This is what we call a decimal place value system, and it's very similar to the one we use today. We too use numbers from 1 to 9, and we use their position to indicate whether it's units, tens, hundreds or thousands. But the power of these rods is that it makes calculations very quick. In fact, the way the ancient Chinese did their calculations is very similar to the way we learn today in school.
Not only were the ancient Chinese the first to use a decimal place value system, but they did so over 1,000 years before we adopted it in the West. But they only used it when calculating with the rods. When writing the numbers down, the ancient Chinese didn't use the place value system. Instead, they used a far more laborious method, in which special symbols stood for tens, hundreds, thousands, and so on. So the number 924 will be written out as 9 hundreds, 2 tens, and 4. Not quite so efficient.
You see, the problem was that the ancient Chinese didn't have a concept of zero. They didn't have a symbol for zero. It just didn't exist as a number. Using the counting rods, they would use a blank space, where today we would write a 0. The problem came with trying to write down this number, which is why they had to create these new symbols for tens, hundreds and thousands. Without a 0, the written number was extremely limited.
But the absence of 0 didn't stop the ancient Chinese from making giant mathematical steps. In fact, there was a widespread fascination with number in ancient China. According to legend, the first sovereign of China, the Yellow Emperor, had one of his deities create mathematics in 2800 BC, believing that number held cosmic significance. And to this day, the Chinese still believe in the mystical power of numbers. Odd numbers are seen as male, even numbers female. The number 4 is to be avoided at all costs. The number 8 brings good fortune. And the ancient Chinese were drawn to patterns in numbers, developing their own rather early version of Sudoku. It was called the Magic Square.
Legend has it that thousands of years ago, Emperor Yu was visited by a sacred turtle that came out of the depths of the Yellow River. On its back were numbers arranged into a magic square, a little like this.
In this square, which was regarded as having great religious significance, all the numbers in each line, horizontal, vertical, and diagonal, all add up to the same number, 15.
Now, the magic square may be no more than a fun puzzle, but it shows the ancient Chinese fascination with mathematical patterns. And it wasn't too long before they were creating even bigger magic squares with even greater magical and mathematical powers.
But mathematics also played a vital role in the running of the emperor's court. the calendar and the movement of the planets were of the utmost importance to the emperor, influencing all his decisions, even down to the way his day was planned. So astronomers became prize members of the imperial court. And astronomers were always mathematicians.
Everything in the emperor's life was governed by the calendar, and he ran his affairs with mathematical precision. The emperor even got his mathematical advisors to come up with a system to help him sleep his way through the vast number of women he had in his harem. Never one to miss a trick, the mathematical advisors decided to base the harem on a mathematical idea called a geometric progression. Maths has never had such a fun purpose.
Legend has it that in the space of 15 nights, the emperor had to sleep with 121 women. The empress, 3 senior consorts, 9 wives, 27 concubines, and 81 slaves. The mathematicians would soon have realised that this was a geometric progression, a series of numbers in which you get from one number to the next by multiplying by the same number each time, in this case 3. Each group of women is 3 times as large as the previous group. So the mathematicians could quickly draw up a rota to ensure that in the space of 15 nights, the emperor slept with every woman in the harem. The first night was reserved for the empress. The next was for the 3 senior consorts. The 9 wives came next. And then the 27 concubines were chosen in rotation, 9 each night. And then finally, over a period of 9 nights, the 81 slaves were dealt with in groups of 9.
Being the emperor certainly required stamina, a bit like being a mathematician. But the object is clear: to procure the best possible imperial succession. The rota ensured that the emperor, or male force.
The emperor's court wasn't alone in its dependence on mathematics. It was central to the running of the state. Ancient China was a vast and growing empire with a strict legal code, widespread taxation, and a standardized system of weights, measures, and money. The empire needed a highly trained civil service, competent in mathematics. And to educate these civil servants was a mathematical textbook probably written in around 200 BC, the 9 chapters. The book is a compilation of 246 problems in practical areas such as trade, payment of wages, and taxes. And at the heart of these problems lies one of the central themes of mathematics: how to solve equations.
Equations are a little bit like cryptic crosswords. You're given a certain amount of information about some unknown numbers, and from that information you've got to deduce what the unknown numbers are. For example, with my weights and scales, I found out that 1 plum, together with 3 peaches, weighs a total of 15 grams. But 2 plums, together with 1 peach, weighs a total of 10 grams. From this information, I can deduce what a single plum weighs and a single peach weighs, and this is how I do it.
If I take the first set of scales, 1 plum and 3 peaches weighing 15 grams, and double it, I get 2 plums and 6 peaches weighing 30 grams. If I take this and subtract from it the second set of scales, that's 2 plums and a peach weighing 10 grams, I'm left with an interesting result: no plums.
Having eliminated the plums, I've discovered that 5 peaches weighs 20 grams. So, a single peach weighs 4 grams. And from this, I can deduce that the plum weighs 3 grams.
the ancient Chinese went on to apply similar methods to larger and larger numbers of unknowns, using it to solve increasingly complicated equations.
What's extraordinary is that this particular system of solving equations didn't appear in the West until the beginning of the 19th century. In 1809, while analysing a rock called Pallas in the asteroid belt, Carl Friedrich Gauss, who would become known as the Prince of Mathematics, rediscovered this method, which had been formulated in ancient China centuries earlier. Once again, ancient China streets ahead of Europe.
But the Chinese were to go on to solve even more complicated equations, involving far larger numbers. In what's become known as the Chinese remainder theorem, the Chinese came up with a new kind of problem. In this, we know the number that's left when the unknown number in the equation is divided by a given number, say 3, 5 or 7. Of course, this is a fairly abstract mathematical problem, but the ancient Chinese still managed to couch it in practical terms.
So, a woman in the market has a tray of eggs, but she doesn't know how many eggs she's got. What she does know is that if she arranges them in threes, she has 1 egg left over. If she arranges them in fives, she gets 2 eggs left over. But if she arranged them in rows of 7, she found she had 3 eggs left over. The ancient Chinese found a systematic way to calculate that the smallest number of eggs she could have had in the tray is 52. But the more amazing thing is that you can capture such a large number like 52 by using these small numbers like 3, 5 and 7. This way of looking at numbers will become a dominant theme in mathematics over the last 2 centuries.
By the 6th century AD, the Chinese remainder theorem was being used in ancient Chinese astronomy to measure planetary movement. But today it still has practical uses. Internet cryptography encodes numbers using mathematics that has its origins in the Chinese remainder theorem. By the 13th century, mathematics was a long-established part of the curriculum, with over 30 mathematics schools scattered across the country. The golden age of Chinese maths had arrived. And its most important mathematician was called Qin Ju Shao. Legend has it that Qin Ju Shao was something of a scoundrel. He was a fantastically corrupt imperial administrator who crisscrossed China, lurching from one post to another. Repeatedly sacked for embezzling government money, he poisoned anyone who got in his way.
Qin Ju Shao was reputedly described as violent as a tiger or a wolf, and as poisonous as a scorpion or a viper. So, not surprisingly, he made a fierce warrior. For 10 years he fought against the invading Mongols, but for much of that time he was complaining that his military life took him away from his true passion. No, not corruption, but mathematics.
Qin started trying to solve equations that grew out of trying to measure the world around us. Quadratic equations involve numbers that are squared, or to the power of 2, say 5 times 5. The ancient Mesopotamians had already realised that these equations were perfect for measuring flat, 2-dimensional shapes, like Tiananmen Square. But Qin was interested in more complicated equations, cubic equations. These involve numbers which are cubed, or to the power of 3, say 5 times 5 times 5. And they were perfect for capturing 3-dimensional shapes, like Chairman Mao's mausoleum. Qin found a way of solving cubic equations, and this is how it worked. Say Qin wants to know the exact dimensions of Chairman Mao's mausoleum. he knows the volume of the building and the relationships between the dimensions. In order to get his answer, Qin uses what he knows to produce a cubic equation. He then makes an educated guess at the dimensions. Although he's captured a good proportion of the mausoleum, there are still bits left over. Qin takes these bits and creates a new cubic equation. He can now refine his first guess by trying to find a solution to this new cubic equation, and so on. Each time he does this, the pieces he's left with get smaller and smaller, and his guesses get better and better.
What's striking is that Qin's method for solving equations wasn't discovered in the West until the 17th century, when Isaac Newton came up with his own, very similar approximation method.
The power of this technique is that it can be applied to even more complicated equations. Qin even used his techniques to solve an equation involving numbers up to the power of 10. This was extraordinary stuff, highly complex mathematics.
Now, Qin may have been years ahead of his time, but there was a problem with his technique. It only gave him an approximate solution. Now, that might be good enough for an engineer, but not for a mathematician. Mathematics is an exact science. We like things to be precise. And Qian just couldn't come up with a formula to give him an exact solution to these complicated equations.
China had made great mathematical leaps, but the next great mathematical breakthroughs were to happen in a country lying to the southwest of China. A country that had a rich mathematical tradition that would change the face of maths forever. India's first great mathematical gift lay in the world of number. Like the Chinese, the Indians had discovered the mathematical benefits of the decimal place value system and were using it by the middle of the 3rd century AD. It's been suggested that the Indians learned the system from Chinese merchants travelling through India with their counting rods. Or they may well just have stumbled across it themselves. It's all such a long time ago that it's shrouded in mystery.
We may never know how the Indians came up with their number system, but we do know that they refined and perfected it, creating the ancestors for the 9 numerals we use across the world today. Many rank the Indian system of counting as one of the greatest intellectual innovations of all time, developing into the closest thing we could call a universal language.
But there was one number missing, and it was the Indians who would introduce it to the world. The earliest known recording of this new number dates from the 9th century, though it was probably in practical use for centuries before. This strange new numeral is engraved on the wall of a small temple in the fort of Gwalior in central India.
So here we are, in one of the true holy sites of the mathematical world. And what I'm looking for is in this inscription written on the wall. Up here are some numbers, and here's the new number. It's 0.
It's astonishing to think that before the Indians invented it, there was no number 0. To the ancient Greeks, it simply hadn't existed. To the Egyptians, Mesopotamians, and as we've seen, the Chinese, 0 had been in use, but as a placeholder, an empty space to show a zero inside a number.
The Indians transformed zero from a mere placeholder into a number that made sense in its own right. A number for calculation, for investigation. This brilliant conceptual leap would revolutionise mathematics.
Now, with just 10 digits, 0 to 9, it was suddenly possible to capture astronomically large numbers in an incredibly efficient way.
But why did the Indians make this imaginative leap? Well, we'll never know for sure, but it's possible that the idea and symbol that the Indians used for zero came from calculations they did with stones in the sand. When stones were removed from the calculation, a small round hole was left in its place, representing the movement from something to nothing.
But perhaps there's also a cultural reason for the invention of zero. For the ancient Indians, the concepts of nothingness and eternity lay at the very heart of their belief system.
In the religions of India, the universe was born out of nothingness, and nothingness is the ultimate goal of humanity. So it's perhaps not surprising that a culture that so enthusiastically embraced the void should be happy with the notion of zero.
The Indians even used the word for the philosophical idea of the void, shunya, to represent the new mathematical term zero. In the 7th century, the brilliant Indian mathematician Brahmagupta proved some of the essential properties of zero. Brahmagupta's rules about calculating with zero are taught in schools all over the world to this day. 1 plus 0 equals 1. 1 minus 0 equals 1. 1 times 0 is equal to 0.
But Brahmagupta came a cropper when he tried to do 1 divided by 0. After all, what number times 0 equals 1? It would require a new mathematical concept, that of infinity, to make sense of dividing by 0. And the breakthrough was made by a 12th century Indian mathematician called Bhaskara II. And it works like this. If I take a fruit and I divide it into halves, I get 2 pieces. So 1 divided by half is 2. If I divide it into thirds, I get 3 pieces. So when I divide it into smaller and smaller fractions, I get more and more pieces. So ultimately, when I divide by a piece which is of 0 size, I'll have infinitely many pieces. So for Bhaskara, 1 divided by 0 is infinity.
But the Indians would go further in their calculations with zero. For example, if you take 3 from 3 and get 0, what happens when you take 4 from 3? It looks like you have nothing. But the Indians recognised that this was a new sort of nothing, negative numbers. The Indians called them debts because they were perfect for solving equations like, if I have 3 batches of material and take 4 away, how many have I left?
This may seem odd and impractical, but that was the beauty of Indian mathematics. Their ability to come up with negative numbers and 0 was because they thought of numbers as abstract entities. They weren't just for counting and measuring pieces of cloth. They had a life of their own, floating free of the real world. This led to an explosion of mathematical ideas.
The Indians' abstract approach to mathematics soon revealed a new side to the problem of how to solve quadratic equations. That is, equations including numbers to the power of 2. Brahmagupta's understanding of negative numbers allowed him to see that quadratic equations always have 2 solutions, one of which could be negative.
Brahmagupta went even further, solving quadratic equations with 2 unknowns, a question which wouldn't be considered in the West until 1657, when the French mathematician Fermat challenged his colleagues with the same problem. Little did he know that they'd been beaten to a solution by Brahmagupta 1,000 years earlier.
Brahmagupta was beginning to find abstract ways of solving equations. But astonishingly, he was also developing a new mathematical language to express that abstraction. Brahmagupta was experimenting with ways of writing his equations down, using the initials of the names of different colours to represent unknowns in his equations.
A new mathematical language was coming to life, which would ultimately lead to the X's and Y's which fill today's mathematical journals.
But it wasn't just new notation that was being developed. Indian mathematicians were responsible for making fundamental new discoveries in the theory of trigonometry. The power of trigonometry is that it acts like a dictionary, translating geometry into numbers and back. Although first developed by the ancient Greeks, it was in the hands of the Indian mathematicians that the subject truly flourished. At its heart lies the study of right-angled triangles.
In trigonometry, you can use this angle here to find the ratios of the opposite side to the longest side. There's a function called the sine function, which when you input the angle, outputs the ratio. So for example, in this triangle, the angle is about 30 degrees. So the output of the sine function is a ratio of 1 to 2, telling me that this side is half the length of the longest side.
In the hands of the Indian mathematicians that the subject truly flourished. At its heart lies the study of right-angled triangles.
In trigonometry, you can use this angle here to find the ratios of the opposite side to the longest side. There's a function called the sine function, which when you input the angle, outputs the ratio. So for example, in this triangle, the angle is about 30 degrees. So the output of the sine function is a ratio of 1 to 2, telling me that this side is half the length of the longest side.
The sine function enables you to calculate distances when you're not able to make an accurate measurement. To this day, it's used in architecture and engineering. The Indians used it to survey the land around them, navigate the seas, and ultimately chart the depths of space itself. It was central to the work of observatories like this one in Delhi, where astronomers would study the stars.
The Indian astronomers could use trigonometry to work out the relative distance between the Earth and the Moon and the Earth and the Sun. You can only make the calculation when the Moon is half full, because that's when it's directly opposite the Sun. So the Sun, Moon and Earth create a right-angled triangle.
Now the Indians could measure that the angle between the Sun and the observatory was 1/7 of a degree. The sine function of 1/7 of a degree gives me the ratio of 400 to 1.
This means that the Sun is 400 times further from the Earth than the Moon is. So, using trigonometry, the Indian mathematicians could explore the solar system without ever having to leave the surface of the Earth.
The ancient Greeks had been the first to explore the sine function, listing precise values for some angles. But they couldn't calculate the sines of every angle. the Indians were to go much further, setting themselves a mammoth task. The search was on to find a way to calculate the sine function of any angle you might be given. The breakthrough in the search for the sine function of every angle would be made here in Kerala in South India. In the 15th century, this part of the country became home to one of the most brilliant schools of mathematicians to have ever worked. Their leader was called Madhava, and he was to make some extraordinary mathematical discoveries.
The key to Madhava's success was the concept of the infinite. Madhava discovered that you could add up infinitely many things with dramatic effects. Previous cultures had been nervous of these infinite sums, but Madhava was happy to play with them. For example, here's how 1 can be made up by adding infinitely many fractions.
I'm heading from 0 to 1 on my boat, but I can split my journey up into infinitely many fractions. So I can get to a half. Then I can sail on a quarter, then an eighth, then a 16th, and so on. The smaller the fractions I move, the nearer to 1 I get. But I'll only get there once I've added up infinitely many fractions.
Now, physically and philosophically, it seems rather a challenge to add up infinitely many things. But that's the power of mathematics, to make sense of the impossible. By producing a language to articulate and manipulate the infinite, you can prove that after infinitely many steps, you'll reach your destination.
Such infinite sums are called infinite series, and Madhava was doing a lot of research into the connections between these series and trigonometry. First, he realised that he could use the same principle of adding up infinitely many fractions to capture one of the most important numbers in mathematics, pi. Pi is the ratio of the circle's circumference to its diameter. It's a number that appears in all sorts of mathematics, but is especially useful for engineers because any measurements involving curves soon require pi. So for centuries, mathematicians searched for a precise value for pi.
It was in 6th century India that the mathematician Aryabhata gave a very accurate approximation for pi, namely 3.1416. He went on to use this to make a measurement of the circumference of the Earth, and he got it as 24,835 miles, which amazingly is only 70 miles away from its true value. But it was in Kerala in the 15th century that Madhava realised he could use infinity to get an exact formula for pi.
By successively adding and subtracting different fractions, Madhava could hone in on an exact formula for pi. First, he moved 4 steps up the number line. That took him way past pi. So next, he took 4/3 of a step, or 1 1/3 steps, back. Now he'd come too far the other way. So he headed forward 4/5 of a step. Each time he alternated between 4 divided by the next odd number. 4/7, 4/9, 4/11, and so on. He zigzagged up and down the number line, getting closer and closer to pi. He discovered that if you went through all the odd numbers, infinitely many of them, you would hit pi exactly.
I was taught at university that this formula for pi was discovered by the 17th century German mathematician Leibniz. But amazingly, it was actually discovered here in Kerala 2 centuries earlier by Madhava. He went on to use the same sort of mathematics to get infinite series expressions for the sine formula in trigonometry. And the wonderful thing is that you can use these formulas now to calculate the sine of any angle to any degree of accuracy.
It seems incredible that the Indians made these discoveries centuries before Western mathematicians. And it says a lot about our attitude in the West to non-Western cultures that we've nearly always claimed their discoveries as our own.
What is clear is the West has been very slow to give due credit to the major breakthroughs made in non-Western mathematics. Madhava wasn't the only mathematician to suffer this way. As the West came into contact more and more with the East during the 18th and 19th centuries, there was a widespread dismissal and denigration of the cultures they were colonising. The natives, it was assumed, couldn't have anything of intellectual worth to offer the West. It's only now, at the beginning of the 21st century, that history is being rewritten.
But Eastern mathematics was to have a major impact in Europe, thanks to the development of one of the major powers of the medieval world. In the 7th century, a new empire began to spread across the Middle East. The teachings of the Prophet Muhammad inspired a vast and powerful Islamic empire, which soon stretched from India in the east to here in Morocco in the west. And at the heart of this empire lay a vibrant intellectual culture. A great library and centre of learning was established in Baghdad. Called the House of Wisdom, its teachings spread throughout the Islamic Empire, reaching schools like this one here in Fez. Subjects studied included astronomy, medicine, chemistry, zoology, and mathematics.
The Muslim scholars collected and translated many ancient texts, effectively saving them for posterity. In fact, without their intervention, we may never have known about the ancient cultures of Egypt, Babylon, Greece and India. But the scholars at the House of Wisdom weren't content simply with translating other people's mathematics. They wanted to create a mathematics of their own, to push the subject forward.
Such intellectual curiosity was actively encouraged in the early centuries of the Islamic Empire. The Quran asserted the importance of knowledge. Learning was nothing less than a requirement of God.
In fact, the needs of Islam demanded mathematical skill. The devout needed to calculate the time of prayer and the direction of Mecca to pray towards. And the prohibition of depicting the human form meant that they had to use much more geometric patterns to cover their buildings. In fact, the Muslim artists discovered all the different sorts of symmetry that you can depict on a two-dimensional wall.
The director of the House of Wisdom in Baghdad was a Persian scholar called Muhammad al-Khwarizmi. Al-Khwarizmi was an exceptional mathematician who was responsible for introducing two key mathematical concepts to the West.
Al-Khwarizmi recognized the incredible potential that the Hindu numerals had to revolutionize mathematics and science. His work explaining the power of these numbers to speed up calculations and do things effectively was so influential that it wasn't long before they were adopted as the numbers of choice amongst the mathematicians of the Islamic world. In fact, these numbers have now become known as the Hindu Arabic numerals.
These numbers, 1 to 9 and 0, are the ones we use today all over the world. But Al-Khwarizmi was to create a whole new mathematical language. It was called algebra and was named after the title of his book, Al-Jabra wa al-Makbal, or calculation by restoration or reduction. Algebra is the grammar that underlies the way that numbers work. It's a language that explains the patterns that lie behind the behaviour of numbers. It's a bit like a code for running a computer program. The code will work whatever the numbers you feed into the program.
For example, mathematicians might have discovered that if you take a number and square it, that's always one more than if you take the numbers either side and multiply those together. For example, 5 times 5 is 25, which is one more than 4 times 6, 24. 6 times 6 is always one more than 5 times 7, and so on. But how can you be sure that this is going to work whatever numbers you take? To explain the pattern underlying these calculations, let's use the dyeing holes in this tannery.
If we take a square of 25 holes running 5 by 5 and take one row of 5 away and add it to the bottom, we get 6 by 4 with 1 left over. But however many holes there are on the side of the square, we can always move one row of holes down in a similar way to be left with a rectangle of holes with 1 left over.
Algebra was a huge breakthrough. Here was a new language to be able to analyse the way that numbers worked. Previously, the Indians and the Chinese had considered very specific problems, but Al-Khwarizmi went from the specific to the general. He developed systematic ways to be able to analyse problems so that the solutions would work whatever the numbers that you took. This language is the one that's used across the mathematical world today.
Al-Khwarizmi's great breakthrough came when he applied algebra to quadratic equations. That is, equations including numbers to the power of 2. The ancient Mesopotamians had devised a cunning method to solve particular quadratic equations. But it was Al-Khwarizmi's abstract language of algebra that could finally express why this method always worked. This was a great conceptual leap, and would ultimately lead to a formula that could be used to solve any quadratic equation, whatever the numbers involved. The next mathematical holy grail was to find a general method that could solve all cubic equations, equations including numbers to the power of 3. It was an 11th century Persian mathematician who took up the challenge of cracking the problem of the cubic. His name was Omar Khayyam, and he travelled widely across the Middle East, calculating as he went. But he was famous for another, very different reason. Khayyam was a celebrated poet, author of the great epic poem, the Rubaiyat.
Now, it may seem a bit odd that a poet was also a master mathematician. After all, the combination doesn't immediately spring to mind. But in fact, there's quite a lot of similarity between the two disciplines. Poetry, with its rhyming structure and rhythmic patterns, resonates quite strongly with constructing a logical mathematical proof.
Khayyam's major mathematical work was devoted to finding the general method to solve all cubic equations. Rather than looking at particular examples, Khayyam carried out a systematic analysis of the problem, true to the algebraic spirit of Al-Khwarizmi.
Khayyam's analysis revealed for the first time that there were several different sorts of cubic equation. But what held him back is that he was still very influenced by the geometric heritage of the Greeks. He couldn't separate the algebra from the geometry. In fact, he wouldn't even consider equations in higher degrees because they described geometric objects in more than 3 dimensions, something he regarded as impossible. Although the geometry allowed him to analyse these cubic equations to some extent, he still couldn't come up with a purely algebraic solution.
It would be another 500 years before mathematicians could make the leap and find a general solution to the cubic equation. And that leap would finally be made in the West, in Italy. During the centuries in which China, India and the Islamic Empire had been in the ascendant, Europe had fallen under the shadow of the Dark Ages. All intellectual life, including the study of mathematics, had stagnated. But by the 13th century, things were beginning to change. Led by Italy, Europe was starting to explore and trade with the East. And with that contact came the spread of Eastern knowledge to the West. It was the son of a customs official that would become Europe's first great medieval mathematician. As a child, he travelled around North Africa with his father, where he learnt about the developments of Arabic mathematics, and especially the benefits of the Hindu-Arabic numerals. When he got home to Italy, he wrote a book that would be hugely influential in the development of Western mathematics. The mathematician was called Leonardo of Pisa, better known as Fibonacci. And in his Book of Calculating, Fibonacci promoted the new number system, demonstrating how simple it was compared to the Roman numerals that were in use across Europe. Calculations were far easier, a fact that had huge consequences for anyone dealing with numbers. Pretty much everyone, from mathematicians to merchants. But there was widespread suspicion of these new numbers. Old habits die hard, and the authorities just didn't trust them. Some believed that they would be more open to fraud, that you could tamper with them. Others believed that they'd be so easy to use for calculations that it would empower the masses, taking authority away from the intelligentsia, who knew how to use the old sort of numbers. The city of Florence even banned them in 1299. But over time, common sense prevailed. The new system spread throughout Europe, and the old Roman system slowly became defunct. At last, the Hindu-Arabic... But over time, common sense prevailed. The new system spread throughout Europe, and the old Roman system slowly became defunct. At last, the Hindu-Arabic numerals 0 to 9 had triumphed. Today, Fibonacci is best known for the discovery of some numbers now called the Fibonacci sequence. The numbers arose when he was trying to solve a riddle about the mating habit of rabbits. Suppose a farmer has a pair of rabbits. Now, rabbits take 2 months to reach maturity, and after that they give birth to another pair of rabbits each month. So the problem was how to determine how many pairs of rabbits there will be in any given month. Well, during the first month, you have 1 pair of rabbits. And since they haven't matured, they can't reproduce. During the second month, there's still only 1 pair. But at the beginning of the third month, the first pair reproduces for the first time, so there are 2 pairs of rabbits. At the beginning of the fourth month, the first pair reproduces again, but the second pair is not mature enough, so there are 3 pairs. In the 5th month, the first pair reproduces, and the second pair reproduces for the first time, but the third pair is still too young, so there are 5 pairs. The mating ritual continues. But what you soon realise is the number of pairs of rabbits you have in any given month is the sum of the pairs of rabbits that you've had in each of the 2 previous months. So the sequence goes 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. The Fibonacci numbers are nature's favourite numbers. It's not just rabbits that use them.
If you count the number of petals on a flower, it's invariably a Fibonacci number. You find these numbers running up and down pineapples if you count the number of segments. Even snails use them to grow their shells. Wherever you find growth in nature, you find the Fibonacci numbers.
But the next major breakthrough in European mathematics wouldn't happen until the early 16th century. It would involve finding the general method that would solve all cubic equations. And it would happen here in the Italian city of Bologna. The University of Bologna was the crucible of European mathematical thought at the beginning of the 16th century. Pupils from all over Europe flocked here and developed a new form of spectator sport, the mathematical competition. Large audiences would gather to watch mathematicians challenge each other with numbers, a kind of intellectual fencing match. But even in this questioning atmosphere, it was believed that some problems were just unsolvable. It was generally assumed that finding a general method to solve all cubic equations was impossible. But one scholar was to prove everyone wrong.
His name was Tartaglia, but he certainly didn't look the heroic architect of a new mathematics. At the age of 12, he'd been slashed across the face with a sabre by a rampaging French army. The result was a terrible facial scar and a devastating speech impediment. In fact, Tartaglia was the nickname he'd been given as a child, and means the stammerer.
Shunned by his schoolmates, Tartaglia lost himself in mathematics. And it wasn't long before he'd found the formula to solve one type of cubic equation. But Tartaglia soon discovered that he wasn't the only one to believe he'd cracked the cubic. A young Italian called Fior was boasting that he too held the secret formula for solving cubic equations. When news broke about the discoveries made by the two mathematicians, a competition was arranged to pit them against each other. The intellectual fencing match of the century was about to begin.
The trouble was that Tartaglia only knew how to solve one sort of cubic equation, and Fior was ready to challenge him with questions about a different sort. But just a few days before the contest, Tartaglia worked out how to solve this different sort, and with this new weapon in his arsenal, he thrashed his opponent, solving all the questions in under 2 hours.
Tartaglia went on to find the formula to solve all types of cubic equations. News soon spread, and a mathematician in Milan called Cardano became so desperate to find the solution that he persuaded a reluctant Tartaglia to reveal the secret to him. But on one condition: that Cardano keep the secret and never publish.
But Cardano couldn't resist discussing Tartaglia's solution with his brilliant student Ferrari. As Ferrari got to grips with Tartaglia's work, he realised that he could use it to solve the more complicated quartic equation, an amazing achievement. Cardano couldn't deny his student his just rewards, and he broke his vow of secrecy, publishing Tartaglia's work together with Ferrari's brilliant solution of the quartic.
Poor Tartaglia never recovered and died penniless. And to this day, the formula that solves the cubic equation is known as Cardano's formula. Tartaglia may not have won glory in his lifetime, but his mathematics managed to solve a problem that had bewildered the great mathematicians of China, India, and the Arab world. It was the first great mathematical breakthrough to happen in modern Europe.
The Europeans now had in their hands the new language of algebra, the powerful techniques of the Hindu-Arabic numerals, and the beginnings of the mastery of the infinite.
It was time for the Western world to start writing its own mathematical stories in the language of the East. The mathematical revolution was about to begin. You can learn more about the story of maths with the Open University at open2.net.
Tomorrow at 8 here on BBC4, we take a look at the mathematics of chaos, unravelling our complex times in high anxieties. Back to tonight, though, and Storyville takes on the story of one of Hollywood's most controversial directors, Roman Polanski. Next.
I'm walking in the mountains of the moon. I'm on the trail of the Renaissance artist Piero della Francesca, and so I've come to the town in northern Italy which Piero made his own.
There it is, Urbino. I've come here to see some of Piero's finest works, masterpieces of art, but also masterpieces of mathematics.
The artists and architects of the early Renaissance brought back the use of perspective, a technique that had been lost for 1,000 years. But using it properly turned out to be a lot more difficult than they imagined. Piero was the first major painter to fully understand perspective, and that's because he was a mathematician as well as an artist. I came here to see his masterpiece, The Flagellation of Christ, but there was a problem.
I've just been to see the flagellation and it's an absolutely stunning picture. But unfortunately, for various kind of Italian reasons, we're not allowed to go and film in there. But this is a maths programme after all and not an arts programme. So I've used a bit of mathematics to bring this picture alive.
We can't go to the picture, but we can make the picture come to us. The problem of perspective is how to represent the three-dimensional world on a two-dimensional canvas. To give a sense of depth, a sense of the third dimension, Piero used mathematics. How big is he going to paint Christ? If this group of men here are a certain distance away from these men in the foreground. Get it wrong, and the illusion of perspective is shattered. It's far from obvious how a three-dimensional world can be accurately represented on a two-dimensional surface. Look at how the parallel lines in a three-dimensional world are no longer parallel in the two-dimensional canvas, but meet at a vanishing point. And this is what the tiles in the picture really look like.
What is emerging here is a new mathematical language which allows us to map one thing into another. The power of perspective unleashed a new way to see the world. A perspective that would cause a mathematical revolution.
Piero's work was the beginning of a new way to understand geometry. But it would take another 200 years before other mathematicians would continue where he left off. Our journey has come north. By the 17th century, Europe had taken over from the Middle East as the world's powerhouse of mathematical ideas. Great strides have been made in the geometry of objects fixed in time and space. In France, Germany, Holland and Britain, the race was now on to understand the mathematics of objects in motion. And the pursuit of this new mathematics started here, in this village in the centre of France. Only the French would name a village after a mathematician. Imagine it in England, a town called Newton, or Boole, or Cayley. I don't think so. But in France, they really value their mathematicians. This is the village of Descartes in the Loire Valley. It was renamed after the famous philosopher and mathematician 200 years ago. Descartes himself was born here in 1596, a sickly child who lost his mother when very young. So he was allowed to stay in bed every morning until 11 a.m., a practice he tried to continue all his life.
To do mathematics, sometimes you just need to remove all distractions and to float off into a world of shapes and patterns. Descartes thought that the bed was the best place to achieve this meditative state, and I think I know what he means.
The house where Descartes undertook his bedtime meditations is now a museum dedicated to all things Cartesian.
Come with me.
Its exhibition pieces, arranged by curator Sylvia Garnier, show how his philosophical, scientific and mathematical ideas all fit together. It also features less familiar aspects of Descartes' life and career.
So he decided to be a soldier in the army, in the Protestant army, and in the Catholic army. No problem for him, because no patriotism.
Sylvia is putting it very nicely, but Descartes was in fact a mercenary. He fought for the German Protestants, the French Catholics, and anyone else who would pay him. Very early one autumn morning in 1628, he was in the Bavarian army, camped out on a cold riverbank.
Inspiration very often strikes in very strange places. A story is told how Descartes couldn't sleep one night, maybe because he was getting up so late, or perhaps he was celebrating St. Martin's Eve and had just drunk too much. Anyway, problems were tumbling around in his mind. He was thinking about his favourite subject, philosophy, but he was finding it very frustrating. How can you actually know anything at all?
Then he slips into a dream. And in the dream, he understood that the key was to build philosophy on the indisputable facts of mathematics. Numbers, he realised, could brush away the cobwebs of uncertainty. He wanted to publish all his radical ideas, but he was worried how they'd be received in Catholic France. So he packed his bags and left. Descartes found a home here in Holland. He'd been one of the champions of the new scientific revolution, which rejected the dominant view that the sun went round the earth, an opinion that had got scientists like Galileo into deep trouble with the Vatican. Descartes reckoned that here amongst the Protestant Dutch, he would be safe, especially at the old university town of Leiden, where they valued maths and science. I've come to Leiden too. Unfortunately, I'm late.
Hello. Yeah, I'm sorry I'm so late. I got a puncture, so it took me a bit of time. Yeah. So
Henk Bos is one of Europe's most eminent Cartesian scholars. He's not surprised the French scholar ended up in Leiden.
He came to talk with people, and some people were open to his ideas. This was not only mathematics, it was also mechanics, especially. He merged algebra and geometry.
Right.
So you could have formulas and figures and go back and forth.
So a sort of dictionary between the two provides...
Yeah.
This dictionary, which was finally published here in Holland in 1637, included mainly controversial philosophical ideas. But the most radical thoughts were in the appendix, a proposal to link algebra and geometry. Each point in 2 dimensions can be described by 2 numbers, one giving the horizontal location, the second number giving the point's vertical location. As the point moves around a circle, these coordinates change. But we can write down an equation that identifies the changing value of these numbers at any point in the figure. Suddenly, geometry has turned into algebra. Using this transformation from geometry into numbers, you could tell, for example, if the curve on this bridge was part of a circle or not. You didn't need to use your eyes. Instead, the equations of the curve would reveal its secrets. But it wouldn't stop there. Descartes had unlocked the possibility of navigating geometries of higher dimensions, worlds our eyes will never see, but are central to modern technology and physics. There's no doubt that Descartes was one of the giants of mathematics. Unfortunately, though, he wasn't the nicest of men.
I think he was not an easy person. So, and he was very much concerned about his image. He was entirely self-convinced that he was right, also when he was wrong. And his first reaction would be that the other one was stupid and hadn't understood it.
Descartes may not have been the most congenial person, but there's no doubt that his insight into the connection between algebra and geometry transformed mathematics forever. For his mathematical revolution to work, though, he needed one other vital ingredient. To find that, I had to say goodbye to Henk and Leiden and go to church. I'm not a believer myself, but there's little doubt that many mathematicians from the time of Descartes had strong religious convictions.
Maybe it's just a coincidence, but perhaps it's because mathematics and religion are both building ideas upon an undisputed set of axioms. 1 + 1 = 2. God exists. I think I know which set of axioms I'd put my faith in.
In the 17th century, there was a Parisian monk who went to the same school as Descartes. He loved mathematics as much as he loved God. Indeed, he saw maths and science as evidence of the existence of God. Marin Mersenne was a first-class mathematician. One of his discoveries in prime numbers is still named after him. But he is also celebrated for his correspondence.
From his monastery in Paris, Mersenne acted like some kind of 17th century internet hub, receiving ideas and then sending them on. It's not so different now. We sit like mathematical monks thinking about our ideas, then sending a message to a colleague and hoping for some reply.
There was a spirit of mathematical communication in 17th century Europe which had not been seen since the Greeks. Mersenne urged people to read Descartes' new work on geometry. He also did something just as important. He publicised some new findings on the properties of numbers by an unknown amateur who would end up rivaling Descartes as the greatest mathematician of his time, Pierre de Fermat. Here in Beaumont-de-Lomagne, near Toulouse, residents and visitors have come out to celebrate the life and work of the village's most famous son. But I'm not too sure what these gladiators are doing here. And the appearance of this camel came as a bit of a surprise too. The man himself would have hardly approved of the ideas of using fun and games to advance an interest in mathematics. Unlike the aristocratic Descartes, Fermat wouldn't have considered it worthless or common to create a festival of mathematics.
Maths in action, that one. It's beautiful. It's really nice, yeah.
Fermat's greatest contribution to mathematics was to virtually invent modern number theory. He devised a wide range of conjectures and theorems about numbers, including his famous last theorem, the proof of which would puzzle mathematicians for over 350 years. But it's little help to me now.
Getting it apart is the easy bit. It's putting it together, isn't it? That's the difficult bit. Okay, how many bits have I got? I got 6 bits. I think what I need to do is put some symmetry into this. I'm afraid he's going to tell me how to do it, and I don't want to see. I hate being told how to do a problem. I'm not going to look. And he's laughing at me now, because I can't do it. That's very unfair. There we go. Can I put them together? J'arrive! I got it! Now that's the buzz of doing mathematics, when the thing clicks together and suddenly you see the right answer.
Remarkably, Fermat only tackled mathematics in his spare time. By day, he was a magistrate. Battling with mathematical problems was his hobby and his passion.
The wonderful thing about mathematics is that you can do it anywhere. You don't have to have a laboratory. You don't even really need a library. Fermat used to do much of his work while sitting at the kitchen table, or praying in his local church, or up here on his roof.
He may have looked like an amateur, but he took his mathematics very seriously indeed. Fermat managed to find several new patterns in numbers that had defeated mathematicians for centuries.
One of my favourite theorems of Fermat is all to do with prime numbers. If you've got a prime number, which when you divide it by 4 leaves remainder 1, then Fermat showed that you could always rewrite this number as 2 square numbers added together. For example, I've got 13 cloves of garlic here, a prime number which has remainder 1 when I divide it by 4. Fermat proved you could rewrite this number as 2 square numbers added together. So 13 can be rewritten as 3 squared plus 2 squared, or 4 plus 9. The amazing thing is that Fermat proved this will work however big the prime number is. Provided it has remainder 1 on division by 4, you can always rewrite that number as 2 square numbers added together. Oh my God! What I love about this sort of day is the playfulness of mathematics, and Fermat certainly enjoyed playing around with numbers. He loved looking for patterns in numbers. And then the puzzle side of mathematics. He wanted to prove that these patterns would be there forever.
But as well as being the basis for fun and games in the years to come, Fermat's mathematics would have some very serious applications. One of his theorems, his Little Theorem, is the basis of the codes that protect our credit cards on the internet. Technology we now rely on today all comes from the scribblings of a 17th century mathematician. But the usefulness of Fermat's mathematics is nothing compared to that of our next great mathematician. And he comes not from France at all, but from its great rival. In the 17th century, Britain was emerging as a world power. Its expansion and ambitions required new methods of measurement and computation, and that gave a great boost to mathematics. The university towns of Oxford and Cambridge were churning out mathematicians who were in great demand, and the greatest of them was Isaac Newton.
I'm here in Grantham where Isaac Newton grew up, and they're very proud of him here. Have a wonderful statue to him. They've even got a shopping centre, the Isaac Newton Shopping Centre, with a nice Apple logo up there. There's a school where he went to, which has got a nice blue plaque, and there's a museum over here in the town hall. Although actually one of the other famous residents here, Margaret Thatcher, has got as big a display as Isaac Newton. In fact, the Thatcher cups have sold out, and there's loads of Newton ones still left, so I thought I would support mathematics by buying a Newton cup.
And Newton's maths does need supporting.
Newton's obviously very famous around here. Do you know what he's famous for?
No. Discovering gravity.
Gravity?
Gravity, yes.
Gravity?
Apple tree and all that.
Yeah.
Gravity.
Gravity.
And that pretty much summed it up. If people know about Newton's work at all, it is his physics, his laws of gravity and motion, not his mathematics.
You're in a rush, okay. Acceleration, you see, one of Newton's laws.
"8 miles south of Grantham, in the village of Woolsthorpe, where Newton was born, I met up with someone who does share my passion for his mathematics.
This is the house.
Oh wow, beautiful.
Jackie Steddle is a Newton fan, and more than willing to show me around the house where Newton was brought up.
So here is the, well, you might call it the dining room. I'm sure they didn't call that, but the room where they ate, next to the kitchen, and of course there would have been a huge fire in there.
Yes, gosh, I wish it was there now.
His father was an illiterate farmer, but he died shortly before Newton was born. Otherwise, the young Isaac's fate might have been very different.
And here's his room.
Oh, lovely, wow.
As we think.
Well, they preserved it really nicely. It's got a real feel of going back in time.
It does, yes.
I can see he's as scruffy as I am. Look at the state of that bed. That's how I think I left my bed this morning.
Newton hated his stepfather, but it was this man who ensured he became a mathematician rather than a sheep farmer.
I don't think he was particularly remarkable as a child.
Okay, so there's hope for all those kids out there.
Yes, I think he had a sort of average school report. He had very few close friends. I don't feel he's someone I particularly would have wanted to meet. But I do love his mathematics. It's wonderful.
Newton came back to Lincolnshire from Cambridge during the Great Plague of 1665, when he was just 22 years old. In 2 miraculous years here, he developed a new theory of light, discovered gravitation, and scribbled out a revolutionary approach to maths.
I'm going to accelerate this car from 0 to 60 as quickly as I can. Now, the speedometer is showing me that the speed's changing all the time, but this is only an average speed. How can I tell precisely what my speed is at any particular instant? Well, here's how. As the car races along the road, we can draw a graph above the road, where the height above each point on the road records how long it took the car to get to that point. I can calculate the average speed between 2 points A and B on my journey by recording the distance travelled and dividing by the time it took to get between these 2 points. But what about the precise speed at the first point A? If I move point B closer and closer to the first point, I take a smaller and smaller window of time, and the speed gets closer and closer to the true value. But eventually, it looks like I have to calculate 0 divided by 0. The calculus allows us to make sense of this calculation. It enables us to work out the exact speed and also the precise distance travelled at any moment in time.
I mean, it does make sense of things which we take for granted so much.
Yeah.
I mean, things that, you know, if I drop this apple...
Its distance is changing and its speed is changing, and calculus can deal with all of that.
Which is quite in contrast to the Greeks. I mean, Greece is a very static geometry.
Yes, yes, it is.
And here we see...
Yeah.
So, I mean, the calculus is used by every engineer, physicist,
Absolutely,
because
yes.
it can describe the moving world.
Yes, I mean, and it's the only way, really. You can deal with the mathematics of motion or with change.
There's a lot of mathematics in this apple.
Newton's calculus enables us to really understand the changing world, the orbits of planets, the motions of fluids. Through the power of the calculus, we have a way of describing with mathematical precision the complex, ever-changing natural world. But it would take 200 years to realise its full potential. Newton himself decided not to publish, but just to circulate his thoughts among friends. His reputation, though, gradually spread. He became a professor, an MP, and then warden of the Royal Mint here in the City of London.
On his regular trips to the Royal Society from the Royal Mint, he preferred to think about theology and alchemy rather than mathematics. Developing the calculus just got crowded out by all his other interests, until he heard about a rival.
A rival who was also a member of the Royal Society and who came up with exactly the same idea as him, Gottfried Leibniz. Every word Leibniz wrote has been preserved and catalogued in his hometown of Hanover in northern Germany. His actual manuscripts are kept under lock and key, particularly the manuscript which shows how Leibniz also discovered the miracle of calculus shortly after Newton.
What age was he when he wrote
he was 29 years old, and at the time, within 2 months, he developed differential calculus and integral calculus.
Really, in 2 months? So it was all fast and furious when it comes. It's, There's a little scrap of paper over here. What's that one? Is that a letter? Or?
That's a small manuscript, and Leibniz notes, sometimes it happens that in the morning, lying in the bed, I have so many ideas that it takes the whole morning, and sometimes even longer, to note all these ideas and bring them to paper.
Right. Now, I suppose that's beautiful.
I suppose that he liked to lie in the bed in the morning.
A true mathematician. Yeah. Spends his time thinking in bed. And I see you've got some paintings down here. So this is
a painting.
This is what he looked like. Right.
Yeah.
Even though he didn't become quite the 17th century celebrity that Newton did, it wasn't such a bad life. Leibniz worked for the royal family of Hanover and travelled around Europe representing their interests. This gave him plenty of time to indulge in his favourite intellectual pastimes, which were wide even for the time. He devised a plan for reunifying the Protestant and Roman Catholic churches, a proposal for France to conquer Egypt, and contributions to philosophy and logic which are still highly rated today.
He wrote all these letters. I mean, that's absolutely extraordinary. He must have cloned himself. I can't believe there was just one Leibniz, you know.
But Leibniz was not just a man of words. He was also one of the first people to invent practical calculating machines that worked on the binary system, true forerunners of the computer. 300 years later, the engineering department at Leibniz University here in Hanover have put them together following Leibniz's blueprint.
I love all the ball bearings. So these are going to be our zeros and ones. So a ball bearing is a
only
one.
zeros and one.
Yeah.
Now we represent the number 127. In binary, it means that we have the first 7 digits in 1.
Yeah.
And now I give in number 1.
Okay.
Now we add 127 plus 1.
Yeah.
Is 128, which is 2 power 8.
Oh, okay. So there's going to be lots of action.
Would you show this here?
So this is the money shot. So we're going to add 1. Oh, here we go. They're all carrying. So
this 128. This is 2 power 8.
Excellent. So 127 in binary is 1111111, which is all the ball bearings here. To add 1, we need it all gets carried. So this goes to 0, 0, 0, 0, and we have a power of 2 here. So this mechanism gets rid of all the ball bearings that you don't need. It's like pinball, mathematical pinball.
Exactly.
I love this machine.
After a hard day's work, Leibniz often came here, the famous gardens of Herrenhausen, now in the middle of Hanover, but then on the outskirts of the city.
Something about mathematics and walking. I don't know, you've been working at your desk all day, all morning, on some problem, and your head's all fuzzy, and you just need to come and have a walk. You let your subconscious mind kind of take over, and sometimes you get your breakthrough just looking at the trees or whatever. I certainly had some of my best ideas whilst walking my local park, so I'm hoping to get a little bit of inspiration here on Leibniz's local stomping ground.
I didn't get the chance to purge my mind of mathematical challenges, because in the years since Leibniz lived here, someone has built a maze.
Well, there is a mathematical formula for getting out of a maze, which is if you put your left hand on the side of the maze and just keep it there, keep on winding round, you eventually get out. That's the theory, at least. Let's see whether it works.
Leibniz had no such distractions. Within 5 years, he'd worked out the details of the calculus, seemingly independent from Newton, although he knew about Newton's work. But unlike Newton, Leibniz was quite happy to make his work known. And so mathematicians across Europe heard about the calculus first from him and not from Newton. And that's when all the trouble started.
Throughout mathematical history, there have been lots of priority disputes and arguments. May seem a little bit petty and schoolboyish, but we really want our name to be on that theorem. This is our one chance for a little bit of immortality, because that theorem's going to last forever. And that's why we dedicate so much time to trying to crack these things. And somehow we can't believe that somebody else has got it at the same time as us. These are our theorems, our babies, our children, and we don't want to share the credit.
Back in London, Newton certainly didn't want to share credit with Leibniz, who he thought of as a Hanoverian upstart. After years of acrimony and accusation, the Royal Society in London was asked to adjudicate between the rival claims. The Royal Society gave Newton credit for the first discovery of the calculus, and Leibniz credit for the first publication. But in their final judgment, they accused Leibniz of plagiarism. However, that might have had something to do with the fact that the report was written by their president, one Sir Isaac Newton. Leibniz was incredibly hurt. He admired Newton and never really recovered. He died in 1716. Newton lived on another 11 years and was buried in the grandeur of Westminster Abbey. Leibniz's memorial, by contrast, is here in this small church in Hanover. The irony is that it's Leibniz's mathematics which eventually triumphs, not Newton's.
I'm a big Leibniz fan. Quite often
Leibniz's memorial, by contrast, is here in this small church in Hanover. The irony is that it's Leibniz's mathematics which eventually triumphs, not Newton's.
I'm a big Leibniz fan. Quite often revolutions in mathematics are about producing the right language to capture a new vision, and that's what Leibniz was so good at.
Leibniz's notation, his way of writing the calculus, captured its true spirit. It's still the one we use in maths today. Newton's notation was for many mathematicians clumsy and difficult to use. And so while British mathematics loses its way a little, the story of maths switches to the very heart of Europe, Basel. In its heyday in the 18th century, the free city of Basel in Switzerland was the commercial hub of the entire Western world. Around this maelstrom of trade, there developed a tradition of learning, particularly learning which connected with commerce. And one family summed all this up.
It's kind of curious. Artists often have children who are artists. Musicians, their children are often musicians. But us mathematicians, our children don't tend to be mathematicians. I'm not sure why it is.
At least that's my view, although others dispute it. What no one disagrees with is there is one great dynasty of mathematicians, the Bernoullis. In the 18th and 19th centuries, they produced half a dozen outstanding mathematicians, any of whom we'd have been proud to have had in Britain. And they all came from Basel.
You might have great minds like Newton and Leibniz who make these fundamental breakthroughs, but you also need the disciples who take that message, clarify it, realise its implications, and then spread it wide.
The family were originally merchants, and this is one of their houses. It's now part of the University of Basel, and it's been completely refurbished, apart from one room, which has been kept very much as the family would have used it. Dr. Fritz Nagel, keeper of the Bernoulli archive, has promised to show it to me. If we can find it.
No, we are in the wrong floor.
Wrong floor, okay.
Wrong floor.
Right. Look, are these free apples? We can take an apple?
No, wrong mathematician. Eventually, we got there.
So this is where the Bernoullis would have done some of their mathematics of an evening.
I was really just being polite. I'm not sure we should have bothered. The only thing of interest was an old stove.
Now, of the Bernoullis, which is your favourite?
My favourite Bernoulli is Johann I. He is the most smart mathematician. Perhaps his brother Jakob was the mathematician with the deeper insight in the problems, but Johann found elegant solutions.
The brothers didn't like each other much, but both worshipped Leibniz. They corresponded with him, stood up for him against Newton's allies, and spread his calculus throughout Europe.
Leibniz was very happy to found two gifted mathematicians outside of his personal circle of friends who mastered his calculus and could distribute it in the scientific community. That was very important for Leibniz.
And important for maths too. Without the Bernoullis, it would have taken much longer for calculus to become what it is today, a cornerstone of mathematics. At least that is Dr. Nagel's contention, and he's a great Bernoulli fan. Tonight, he's arranged for me to meet Professor Daniel Bernoulli, the latest member of the family, whose famous name ensures he gets some very odd emails.
Another one which I got was Professor Bernoulli, can you give me a hand with calculus?
Yes, exactly. To find a Bernoulli, then you expect them to be able to do some calculus.
But this Daniel Bernoulli is a professor of geology. The maths gene seems to have truly died out. And during our very hearty dinner, I found myself wandering back to maths. It's a bit unfair on the Bernoullis to describe them simply as disciples of Leibniz. One of their many great contributions to mathematics was to develop the calculus to solve a classic problem of the day. Imagine a ball rolling down a ramp. The task is to design a ramp that will get the ball from the top to the bottom in the fastest time possible. You might think that a straight ramp would be quickest, or possibly a curved one like this that gives the ball plenty of downward momentum. In fact, it's neither of these. Calculus shows that it's what we call a cycloid, the path traced by a point on the rim of a moving bicycle wheel. This application of the calculus by the Bernoullis, which became known as the calculus of variation, has become one of the most powerful aspects of the mathematics of Leibniz and Newton. Investors use it to maximize profits. Engineers exploit it to minimize energy use. Designers apply it to optimize construction. It has now become one of the linchpins of our modern technological world. Meanwhile, things were getting more interesting in the restaurant.
My second surprise, may I introduce Mr. Leonhard Euler? Daniel Bernoulli.
Leonhard Euler, one of the most famous names in mathematics. This Leonhard is a descendant of the original Leonhard Euler, star pupil of Johann Bernoulli.
I'm the 9th generation and the 4th Leonhard in our family after Leonhard Euler the first, the mathematician.
Okay, and yourself, are you a mathematician?
Actually, I'm a business analyst. I can't study mathematician with my name.
Everyone will expect you to prove the Riemann hypothesis.
Perhaps it's just as well that Leonhard decided not to follow in the footsteps of his illustrious ancestor. He'd have had a lot to live up to.
I'm going in a boat across the Rhine, and I must say I'm feeling a little bit worse for wear this morning. Last night's dinner with Mr. Euler and Professor Bernoulli degenerated into toasts to all the theorems that the Bernoullis and Eulers had proved, and by God, they proved quite a lot of them. Never again.
I was getting disapproving glances from my fellow passengers as well. Luckily, it was only a short trip. Not like the trip that Euler took in 1728 to start a new life. Euler may have been the prodigy of Johann Bernoulli, but there was no room for him in the city.
If your name wasn't Bernoulli, then there was little chance of getting a job in mathematics here in Basel. But Daniel, the son of Johann Bernoulli, was a great friend of Euler and managed to get him a job at his university.
But to get there would take 7 weeks, because Daniel's university was in Russia. It wasn't an intellectual powerhouse like Berlin or Paris, but St. Petersburg was by no means unsophisticated in the 18th century. Peter the Great had created his city very much in the European style, and every fashionable city at the time had a scientific academy. Peter's Academy is now a museum. It includes several rooms full of the kind of grotesque curiosities that are usually kept out of the public display in the West. But in the 1730s, this building was a centre for groundbreaking research. It's where Euler found his intellectual home.
I'm sure that there could never be a more contented man than me. I earn my living.
Many of the ideas that were bubbling away at the time, calculus of variation, Fermat's theory of numbers, crystallise in Euler's hands. But he was also creating incredibly modern mathematics, topology and analysis.
Much of the notation that I use today as a mathematician was created by Euler, numbers like E and I. Euler also popularised the use of the symbol pi.
He even combined these numbers together in one of the most beautiful formulas of mathematics. E to the power of I times pi is equal to -1, an amazing feat of mathematical alchemy.
His life, in fact, is full of mathematical magic. Euler applied his skills to an immense range of topics, from prime numbers to optics to astronomy. He devised a new system of weights and measures, wrote a textbook on mechanics, and even found time to develop a new theory of music. I think of him as the Mozart of maths, and that view is shared by the mathematician Nikolai Vavilov, who met me at the house that was given to Euler by Catherine the Great.
Euler lived here from 66 to 83, which means from the year he came back to St. Petersburg to the year he died. And he was a member of the Russian Academy of Sciences and the greatest mathematician.
Right.
This is exactly what it says.
What is it now?
Now it's a school, actually.
A school?
Yeah.
Should we go in and see what's...
okay, yeah.
I'm not sure Nikolai entirely approved, but nothing ventured.
Perhaps we should talk to the head teacher and see whether we can...
Здравствуйте, мы пройдем к директору.
The head didn't mind at all. I rather got the impression that she was used to people dropping in to talk about Euler. She even had a couple of very able pupils suspiciously close to hand.
These 2 young ladies.
The head didn't mind at all. I rather got the impression that she was used to people dropping in to talk about Euler. She even had a couple of very able pupils suspiciously close to hand.
These 2 young ladies are ready to tell us a few words about
the scientists and about this very building.
They certainly knew their stuff.
Would you like them to
They'd undertaken an entire classroom project on Euler, his long life, happy marriage, and 13 children. And then his tragedies. Only 5 of his children survived to adulthood. His first wife, who he adored, died young. He started losing most of his eyesight.
So for the last years of his life, he still continued to work, actually. He still continued his mathematical research.
Yeah, I read a lovely quote that said, now with his blindness, he hasn't got any distractions and he can finally get on with his mathematics.
Yeah, this is what he said, yes.
Very positive attitude.
Actually,
It was a totally unexpected and charming visit. Although I couldn't resist sneaking back and correcting one of the equations on the board when everyone else had left. To demonstrate one of my favourite Euler theorems, I needed a drink. It concerns calculating infinite sums, the discovery that shot Euler to the top of the mathematical pops when it was announced in 1735. Take 1 shot glass full of vodka and add it to this tall glass here. Next, take a glass which is a quarter full or a half squared and add it to the first glass. Next, take a glass which is a ninth full or a third squared and add that one. Now, if I keep on adding infinitely many glasses where each one is a fraction squared, how much will be in this tall glass here? It was called the Basel problem after the Bernoullis tried and failed to solve it. Daniel Bernoulli knew that you would not get an infinite amount of vodka. He estimated that the total would come to about 1 3/5. But then Euler came along. Daniel was close, but mathematics is about precision. Euler calculated that the total height of the vodka would be exactly pi squared divided by 6. It was a complete surprise. What on earth did adding squares of fractions have to do with this special number pi? But Euler's analysis showed that they were 2 sides of the same equation. 1 plus a quarter plus a ninth plus a 16th and so on to infinity is equal to pi squared over 6. That's still quite a lot of vodka, but here goes. Euler would certainly be a hard act to follow. Mathematicians from 2 countries would try. Both France and Germany were caught up in the age of revolution that was sweeping Europe in the late 18th century. Both desperately needed mathematicians, but they went about supporting mathematics rather differently. Here in France, the revolution emphasised the usefulness of mathematics. Napoleon recognised that if you were going to have the best military machine, the best weaponry, then you needed the best mathematicians. Napoleon's reforms gave mathematics a big boost, but this was a mathematics that was going to serve society. Here in the German states, the great educationalist Wilhelm von Humboldt was also committed to mathematics, but a mathematics that was detached from the demands of the state and the military. Von Humboldt's educational reforms valued mathematics for its own sake. In France, they got wonderful mathematicians like Joseph Fourier, whose work on sound waves we still benefit from today. MP3 technology is based on Fourier analysis. But in Germany, they got, at least in my opinion, the greatest mathematician ever. Quaint and quiet, the university town of Göttingen may seem like a bit of a backwater. But this little town has been home to some of the giants of maths, including the man who's often described as the prince of mathematics, Carl Friedrich Gauss. Few non-mathematicians, however, seem to know anything about him. Not in Paris, qui s'appelle Carl Friedrich Gauss. No? Not in Oxford.
I've heard the name, but I couldn't tell you.
No idea.
No idea?
No.
And I'm afraid to say, not even in modern Germany.
Me?
No? Okay.
I don't know.
You don't know? But in Göttingen, everyone knows who Gauss is. He's the local hero. His father was a stonemason, and it's likely that Gauss would have become one too. But his singular talent was recognised by his mother, and she helped ensure that he received the best possible education.
Every few years in the news you hear about a new prodigy who's passed their A-levels at 10, gone to university at 12, but nobody compares to Gauss. Already at the age of 12, he was criticising Euclid's geometry. At 15, he discovered a new pattern in prime numbers, which had eluded mathematicians for 2,000 years. And at 19, he discovered a construction of a 17-sided figure, which nobody had known before this time.
His early successes encouraged Gauss to keep a diary. Here at the University of Göttingen, you can still read it, if you can understand Latin. Fortunately, I had help.
The first entry is in 1796. Is it possible to lift it up? Yes, but be careful. It's really one of the most valuable things that this library possesses.
Yeah, I can believe that.
He writes beautifully.
It is aesthetically very pleasing, even if people don't understand what this is. It is just beautiful to look at. I'm going to put this down, actually. It's very delicate.
Yes.
The diary proves that some of Gauss's ideas were 100 years ahead of their time.
And here are some signs and
these are sort of integrals.
Very different sort of mathematics.
This was the first intimations of the theory of elliptic functions, which was one of his other great developments.
So there's already getting very sophisticated.
And here you see something that is basically the Riemann zeta function appearing.
Wow!
Here.
Gosh.
That's very impressive. The zeta function has become a vital element in our present understanding of the distribution of the building blocks of all numbers, the primes.
There is somewhere in the diary here where he says, I've made this wonderful discovery, and incidentally a son was born today.
We see his priorities.
Yes, indeed.
I think I know a few mathematicians like that too. Yes.
My priorities, though, for the rest of the afternoon were clear. I needed another walk. Fortunately, Göttingen is surrounded by good woodland trails. It was a perfect setting for me to think more about Gauss's discoveries.
Gauss's mathematics has touched many parts of the mathematical world, but I'm going to just choose one of them, a fun one, imaginary numbers.
In the 16th and 17th century, European mathematicians imagined the square root of -1 and gave it the symbol I. They didn't like it much, but it solved equations that couldn't be solved any other way.
Imaginary numbers have helped us to understand radio waves, to build bridges and aeroplanes. They're even the key to quantum physics, the science of the subatomic world. They've provided a map to see how things really are.
But back in the early 19th century, they had no map, no picture of how imaginary numbers connected with real numbers.
Where is this new number? There's no room on the number line for the square root of -1. I've got the positive numbers running out here, the negative numbers running here.
The great step is to create a new direction of numbers, perpendicular to the number line. And that's where the square root of -1 is. Gauss was not the first to come up with this two-dimensional picture of numbers, but he was the first person to explain it all clearly. He gave people a picture to understand how imaginary numbers worked. And once they developed this picture, their immense potential could really be unleashed.
Morgen ein Kaffee bitte? Yeah, okay.
His maths led to acclaim and financial security for Gauss. He could have gone anywhere, but he was happy enough to settle down and spend the rest of his life in sleepy Göttingen. Unfortunately, as his fame developed, so his character deteriorated. A naturally conservative, shy man, he became increasingly distrustful and grumpy.
Many young mathematicians across Europe regarded Gauss as a god, and they would send in their theorems, their conjectures, even some proofs. But most of the time he wouldn't respond, and even when he did, it was generally to say either they got it wrong or he'd proved it already.
His dismissal or lack of interest in the work of lesser mortals sometimes discouraged some very talented mathematicians from pursuing their ideas. But occasionally, Gauss also failed to follow up on his own insights, including one very important insight that might have transformed the mathematics of his time. Gauss took on many projects for the Hanoverian government, including the first proper survey of all the lands of Hanover.
Now, was this Gauss's choice to do this surveying? I mean, for a mathematician, it sounds like the last thing I'd want to do. But
he wanted to do it. The major point in doing this was to discover the shape of the Earth.
But he also started speculating about something even more revolutionary: the shape of space.
So he's thinking, you know, there may not be anything flat
exactly.
in the universe.
And, exactly. And if we were living in a curved universe, there wouldn't be anything flat.
And this led Gauss to question one of the central tenets of mathematics, Euclid's geometry. He realised that this geometry, far from universal, depended on the idea of space as flat. It just didn't apply to a universe that was curved. But in the early 19th century, Euclid's geometry was seen as God-given, and Gauss didn't want any trouble. So he never published anything. Another mathematician, though, had no such fears. In mathematics, it's often helpful to be part of a community where you can talk to and bounce ideas off others. But inside such a mathematical community, it can sometimes be difficult to come up with that one idea that completely challenges the status quo. And then the breakthrough often comes from somewhere else.
Mathematics can be done in some pretty weird places. I'm in Transylvania, which is fairly appropriate because I'm in search of a lone wolf.
Janusz Bolyai spent much of his life hundreds of miles away from the mathematical centres of excellence. This is the only portrait of him that I was able to find.
Unfortunately, it isn't actually him. It's one the Communist Party in Romania started circulating when people got interested in Bolyai's theories in the 1960s. But they couldn't find a picture of Janos, so they substituted a picture of somebody else instead.
Born in 1802, Janos was the son of Farkas Bolyai, who was a maths teacher. He realised his son was a mathematical prodigy, so he wrote to his old friend Carl Friedrich Gauss asking him to tutor the boy. Sadly, Gauss declined. So, instead of becoming a professional mathematician, Janos joined the army. But mathematics remained his first love.
Maybe there's something about the air here, because Bolyai carried on doing his mathematics in his spare time. He started to explore what he called imaginary geometries, where the angles in triangles add up to less than 180. The amazing thing is that these imaginary geometries make perfect mathematical sense.
Bolyai's new geometry has become known as hyperbolic geometry. The best way to imagine it is a kind of mirror image of a sphere, where lines curve back on each other. It's difficult to represent it, since we're so used to living in space which appears to be straight and flat. In his hometown of Tirgamoris, I went looking for more about Bolyai's revolutionary mathematics. His memory is certainly revered here. The museum contains a collection of Bolyai-related artefacts, some of which might be considered distinctly Transylvanian.
It's still got some hair on it. It's kind of a little bit gruesome.
But the object I like most here is a beautiful model of Bolyai's geometry.
I mean, you've got the shortest distance between here and here, if you stick on this surface, is not a straight line, but this curved line which sort of bends into the triangle. So here's a surface where the shortest distances which define the triangle add up to less than 180.
Bolyai published his work in 1831, and his father sent his old friend Gauss a copy. Gauss wrote back straight away, giving his approval. But Gauss refused to praise the young Bolyai, because he said the person he should be praising was himself. He'd worked it all out a decade or so before.
Actually, there is a letter from Gauss to another friend of his, where he says that I regard this young geometer Bolyai as a genius of the first order.
But Gauss never thought to tell Bolyai that, and young Janos was completely disheartened. Another body blow soon followed. Somebody else had developed exactly the same idea, but had published 2 years before him, the Russian mathematician Nicholas Lobachevsky.
It was all downhill for Bolyai after that. With no recognition or career, he didn't publish anything else. Eventually, he went a little crazy.
In 1860, János Bolyai died in obscurity. Gauss, by contrast, was lionized after his death. A university, the units used to measure magnetic induction, even a crater on the moon would be named after him. During his lifetime, Gauss lent his support to very few mathematicians. But one exception was another of Göttingen's mathematical giants, Bernhard Riemann. His father was a minister, and he would remain a sincere Christian all his life. But Riemann grew up a shy boy who suffered from consumption. His family was large and poor, and the only thing the young boy had going for him was an excellence at maths. That was his salvation.
Many mathematicians like Riemann had very difficult childhoods, were quite unsociable. Their lives seemed to be falling apart. It was mathematics that gave them a sense of security.
Riemann spent much of his early life in the town of Lüneburg in northern Germany. This was his local school, built as a direct result of Humboldt's educational reforms in the early 19th century. Riemann was one of its first pupils. The head teacher saw a way of bringing out the shy boy.
He was given the freedom of the school's library. It opened up a whole new world to him. One of the books he found in there was a book by the French mathematician Legendre, all about number theory. His teacher asked him how he was getting on with it. He replied, "I've understood all 859 pages of this wonderful book."
It was a strategy that obviously suited Riemann because he became a brilliant mathematician. And one of his most famous contributions to mathematics was a lecture in 1852 on the foundations of geometry. In the lecture, Riemann first described what geometry actually was and its relationship with the world. He then sketched out what geometry could be, and mathematics of many different kinds of space, only one of which would be the flat Euclidean space in which we appear to live. He was just 26 years old.
Was it received well? I mean, did people recognize the revolution?
There was no way that people could actually make these ideas concrete.
Right.
That only occurred 50 years after this, 60 years after this, with Einstein.
With Einstein.
Yes.
So this is the beginning, really, of the revolution which ends with Einstein's relativity.
Exactly, yes, yes.
Riemann's mathematics changed how we see the world. Suddenly, higher dimensional geometry appeared. The potential was there from Descartes, but it was Riemann's imagination that made it happen.
Well, he began without putting any restriction on the dimensions whatsoever. This was something that was actually quite new in his way of thinking about things.
And somebody like Bolyai was really thinking about, new geometries, but new two-dimensional geometries.
New two-dimensional geometries. Right. Riemann then broke away from all the limitations of 2 or 3 dimensions and began to think in higher dimensions.
Right.
And this was quite new.
Yeah.
Multi-dimensional space is at the heart of so much mathematics done today. In geometry, number theory, and several other branches of maths, Riemann's ideas still perplex and amaze. He died, though, in 1866. He was only 39 years old. Today, the results of Riemann's mathematics are everywhere. Hyperspace is no longer science fiction, but science fact. In Paris, they've even tried to visualize what shapes in higher dimensions might look like.
Just as the Renaissance artist Piero would have drawn a square inside a square to represent a cube on the two-dimensional canvas, the architect here at La Défense has built a cube inside a cube to represent a shadow of the four-dimensional hypercube. It is with Riemann's work that we finally have the mathematical glasses to be able to explore such worlds of the mind.
It's taken a while to make these glasses fit, but without this golden age of mathematics, from Descartes to Riemann, there would be no calculus, no quantum physics, no relativity, none of the technology we use today. But even more important than that, their mathematics blew away the cobwebs and allowed us to see the world as it really is, a world much stranger than we ever thought. Mathematics is about solving problems. And it's the great unsolved problems that make maths really alive.
In the summer of 1900, the International Congress of Mathematicians was held here in Paris in the Sorbonne. It was a pretty shambolic affair, not helped by the sultry August heat. But it will be remembered as one of the greatest congresses of all time, thanks to a lecture given by the up-and-coming David Hilbert.
Hilbert, a young German mathematician, boldly set out what he believed were the 23 most important problems for mathematicians to crack. He was trying to set the agenda for 20th century maths, and he succeeded. These Hilbert problems would define the mathematics of the modern age. Of those who tried to crack Hilbert's challenges, some would experience immense triumphs, whilst others would be plunged into infinite despair. The first problem on Hilbert's list emerged from here, Halle in East Germany. It was where the great mathematician George Cantor spent all his adult life, and where he became the first person to really understand the meaning of infinity and give it mathematical precision. The statue in the town square, however, honours Halle's other famous son, the composer George Handel. To discover more about Cantor, I had to take a tram way out of town.
For 50 years, Halle was part of communist East Germany, and the communists loved celebrating their scientists, so much so that they put Cantor on the side of a large cube that they commissioned. But being communists, they didn't put the cube in the middle of the town, they put it out amongst the people.
When I eventually found the estate, I started to fear that maybe I got the location wrong.
So this looks the most unlikely venue for a statue to a mathematician. Excuse me, ein Frage. Can you help me a bit? Do you speak English?
No.
No. Ich suche eine Würfel. Ein Würfel, yeah. Is that right? A Würfel, a cube? Yeah, like that? Mit ein Abbindung der Mathematiker? Yeah, go around there. Die Name ist Cantor. Somewhere over here. Oh, there it is! It's actually much bigger than I thought it was going to be. I thought it was going to be something like this sort of size. Aha! Here we are, on the dark side of the cube. Here's the man himself, Cantor. Cantor is one of my big heroes, actually. I think if I had to choose some theorems that I wish I'd proved, I think the couple that Cantor proves would be up there in my top 10.
And this is because, before Cantor, no one had really understood infinity. It was a tricky, slippery concept that didn't really seem to go anywhere. But Cantor showed that infinity could be perfectly understandable. Indeed, there wasn't just one infinity, but infinitely many infinities. First, Cantor took the numbers 1, 2, 3, 4, and so on. Then he thought about comparing them with a much smaller set, something like 10, 20, 30, 40. What he showed is that these two infinite sets of numbers actually have the same size, because we can pair them up, 1 with 10, 2 with 20, 3 with 30, and so on. So these are the same sizes of infinity.
But what about the fractions? After all, there are infinitely many fractions between any of the two whole numbers.
So surely the infinity of fractions is much bigger than the infinity of whole numbers.
Well, what Cantor did was to find a way to pair up all of the whole numbers with an infinite load of fractions. And this is how he did it.
He started by arranging all the fractions in an infinite grid. The first row contained the whole numbers, fractions with 1 on the bottom. In the second row came the halves, fractions with 2 on the bottom, and so on. Every fraction appears somewhere in this grid. Where's 2/3? Second column, third row. Now imagine a line snaking back and forward diagonally through the fractions. by pulling this line straight, we can match up every fraction with one of the whole numbers. This means the fractions are the same sort of infinity as the whole numbers.
So perhaps all infinities have the same size. Well, here comes the really exciting bit, because Cantor now considers the set of all infinite decimal numbers.
And here he proves that they give us a bigger infinity, because however you try to list all the infinite decimals, Cantor produced a clever argument to show how to construct a new decimal number that was missing from your list. Suddenly, the idea of infinity opens up. There are different infinities, some bigger than others.
It's a really exciting moment. For me, this is like the first humans understanding how to count things. But now we're counting in a different way. We're counting infinities.
A door has opened and an entirely new mathematics lay before us. But it never helped Cantor much. I was in the cemetery in Halle where he's buried, and where I'd arranged to meet Professor Joe Dorban. He was keen to make the connections between Cantor's maths and his life.
He suffered from manic depression. One of the first big breakdowns he has is in 1884.
Right.
But then around the turn of the century, these recurrences of the mental illness become more and more frequent.
A lot of people have tried to make out that his mental illness was somehow triggered by the incredible abstract mathematics that he was dealing with.
Well, he was certainly struggling, so there may have been a connection.
Yeah, I mean, I must say, you know, when you start to contemplate the infinite, you know, I'm pretty happy with sort of the bottom end of the infinite. But as you kind of build it up more and more, I must say I start to feel unnerved by quite what's going on here and where is it going.
For much of Cantor's life, the only place it was going was here, the university's sanatorium. There was no treatment then for manic depression, or indeed for the paranoia that often accompanied Cantor's attacks. Yet the clinic was a good place to be, comfortable, quiet and peaceful. And Cantor often found his time here gave him the mental strength to resume his exploration of the infinite. Other mathematicians would be bothered by the paradoxes that Cantor's work created. Curiously, this was the one thing Cantor was not worried by.
He was never as upset about the paradoxes of the infinite as everybody else was. Because Cantor believed that, all right, there are certain things that I've been able to show we can establish with complete mathematical certainty, and then the absolute infinite, which is only in God, he can understand all of this, and there's still that final paradox that is not given to us to understand, but God does.
But there was one problem that Cantor couldn't leave in the hands of the Almighty, a problem he wrestled with for the rest of his life. It became known as the continuum hypothesis. Is there an infinity sitting between the smaller infinity of all the whole numbers and the larger infinity of the decimals? Cantor's work didn't go down well with many of his contemporaries, but there was one mathematician from France who spoke up for him, arguing that Cantor's new mathematics of infinity was beautiful, if pathological. Fortunately, this mathematician was the most famous and respected mathematician of his day.
When Bertrand Russell was asked by a French politician who he thought the greatest man France had produced, he replied without hesitation, Poincaré. The politician expressed surprise that he'd chosen the Prime Minister, Raymond Poincaré, above the likes of Napoleon, Balzac. Russell replied, I don't mean Raymond Poincaré, but his cousin, the mathematician, Henri Poincaré.
Henri Poincaré spent most of his life in Paris, a city that he loved, even with its uncertain climate. In the last decades of the 19th century, Paris was a centre for world mathematics, and Poincaré became its leading light. Algebra, geometry, analysis, he was good at everything. His work would lead to all kinds of applications, from finding your way around on the underground to new ways of predicting the weather.
Poincaré was very strict about his working day. 2 hours of work in the morning and 2 hours of work in the early evening. It was in between these periods that he would let his subconscious carry on working on the problem. He recalls one moment when he had a flash of inspiration, which occurred to him almost out of nowhere, just as he was getting on a bus.
And one such flash of inspiration led to an early success. In 1885, King Oscar II of Sweden and Norway offered a prize of 2,500 crowns for anyone who could establish mathematically once and for all whether the solar system would continue turning like clockwork or might suddenly fly apart. If the solar system has 2 planets, then Newton had already proved that their orbits would be stable. The 2 bodies just travel around in ellipses around each other. But as soon as you add 3 bodies like the Earth, Moon and Sun, the question of whether their orbits were stable or not stumped even the great Newton. The problem is that now you have some 18 different variables, like the exact coordinates of each body and their velocity in each direction, so the equations become very difficult to solve. But Poincaré made significant headway in sorting them out. Poincaré simplified the problem by making successive approximations to the orbits, which he believed wouldn't affect the final outcome significantly. Although he couldn't solve the problem in its entirety, his ideas were sophisticated enough to win him the prize.
He developed this great sort of arsenal of techniques, mathematical techniques, which in order to try and solve it. And in fact, the prize that he won was essentially really more for the techniques than for solving the problem.
But when Poincaré's paper was being prepared for publication by the king's scientific advisor, Mittag Leffler, one of the editors found a problem. Poincaré realised that he'd made a mistake. Contrary to what he'd originally thought, even a small change in the initial conditions could end up producing vastly different orbits. His simplification just didn't work. But the result was even more important. The orbits Poincaré had discovered indirectly led to what we now know as chaos theory. Understanding the mathematical rules of chaos explain why a butterfly's wings could create tiny changes in the atmosphere that ultimately might cause a tornado or a hurricane to appear on the other side of the world.
So this big subject of the 20th century, chaos, actually came out of a mistake that Poincaré only spotted at the last minute.
And so the essay had actually been published in its original form and was ready to go out. I mean, and in fact, Mittag Leffler had sent copies out to various people. And it was to his horror when Poincaré wrote to him and said, stop,
Oh my God, this is every mathematician's worst nightmare.
Yeah, absolutely, pull it.
Yes, hold the presses.
Absolutely. So in a way, it kind of worked.
Owning up to his mistake, if anything, enhanced Poincaré's reputation. He continued to produce a wide range of original work throughout his life. Not just specialist stuff either. He also wrote popular books extolling the importance of maths.
Here we go, there's a section on the future of mathematics, which starts, if we wish to foresee the future of mathematics, our proper course is to study the history and present the condition of the science. So I think Poincaré might well have approved of my journey to uncover the story of maths.
He certainly would have approved of the next destination, because to discover perhaps Poincaré's most important contribution to modern mathematics, I had to go looking for a bridge. 7 bridges, in fact. The 7 bridges of Königsberg. Today, the city's known as Kaliningrad, a little outpost of Russia on the Baltic Sea, surrounded by Poland and Lithuania. Until 1945, however, when it was ceded to the Soviet Union, it was the great Prussian city of Königsberg. Much of the old town, sadly, has been demolished. There's now no sign at all of 2 of the original 7 bridges, and several have changed out of all recognition.
This is one of the original bridges. It may seem like an unlikely setting for the beginning of a mathematical story, but bear with me.
It started as an 18th century puzzle. Is there a route around the city which crosses each of these 7 bridges only once? Finding the solution is much more difficult than it looks. It was eventually solved by the great mathematician Leonhard Euler, who in 1735 proved that it wasn't possible, There couldn't be a route that didn't cross at least one bridge twice.
He solved the problem by making a conceptual leap. He realised you don't really care what the distances are between these bridges. What really matters is how the bridges are connected together. This is a problem of a new sort of geometry of position, a problem of topology.
Many of us use topology every day. Virtually all metro maps the world over are drawn on topological principles. You don't care how far the stations are from each other, but how they're connected. There isn't a metro in Kaliningrad, but there is in the nearest other Russian city, St. Petersburg.
The topology is pretty easy on this map. It's the Russian I'm having difficulty with. Can you tell me which... what's the problem? I want to know what station this one was? Oh, I had it the wrong way round even.
Although topology had its origins in the bridges of Königsberg, it was in the hands of Poincaré that the subject evolved into a powerful new way of looking at shape. Some people refer to topology as bendy geometry, because in topology, two shapes are the same if you can bend or morph one into another without cutting it. So for example, if I take a football or rugby ball, topologically they're the same, because one can be morphed into the other. Similarly, a bagel and a teacup are the same, because one can be morphed into the other. Even very complicated shapes can be unwrapped to become much simpler from a topological point of view. But there's no way to continuously deform a bagel to morph it into a ball. The hole in the middle makes these shapes topologically different. Poincaré knew all the possible two-dimensional topological surfaces. But in 1904, he came up with a topological problem he just couldn't solve.
If you've got a flat, two-dimensional universe, then Poincaré worked out all the possible shapes you could wrap that universe up into. It could be a ball, or a bagel with one hole, two holes, or more holes in. But we live in a three-dimensional universe, so what are the possible shapes that our universe could be?
That question became known as the Poincaré conjecture. It was finally solved in 2002 here in St. Petersburg by a Russian mathematician called Grisha Perelman. His proof is very difficult to understand, even for mathematicians. Perelman solved the problem by linking it to a completely different area of mathematics. To understand the shapes, he looked instead at the dynamics of the way things can flow over the shape, which led to a description of all the possible ways that three-dimensional space can be wrapped up in higher dimensions. I wondered if the man himself could help in unravelling the intricacies of his proof. But I've been told that finding Perelman is almost as difficult as understanding the solution.
The classic stereotype of the mathematician is a mad, eccentric scientist, but I think that's a little bit unfair. Most of my colleagues are perfectly normal. Well, reasonably.
But when it comes to Perelman, there's no doubt he is a very strange character. He's received prizes and offers of professorships from distinguished universities in the West, but he's turned them all down. Recently, he seems to have given up mathematics completely and retreated to live as a semi-recluse in this very modest housing estate with his mum. He refuses to talk to the media, but I thought he might just talk to me as a fellow mathematician. I was wrong.
Well, it's interesting. I think he's actually turned off his buzzer. Probably too many media have actually been buzzing it, and I've tried a neighbour. That one rang, but his doesn't ring at all. But in some sense, I think that it's his papers, his mathematics, which speaks for itself in a way. I don't really need to meet the mathematician. And in this age of big brother and big money, I think there's something rather noble about the fact that he gets his kick out of proving theorems and not winning prizes.
One mathematician would certainly have applauded. For solving any of his 23 problems, David Hilbert offered no prize or reward beyond the admiration of other mathematicians. When he sketched out the problems in Paris in 1900, Hilbert himself was already a mathematical star. And it was in Göttingen in northern Germany that he really shone.
He was by far the most charismatic mathematician, far the most charismatic mathematician of his age. It's clear that everybody that knew him thought that he was absolutely wonderful. He studied number theory and brought everything together that was there, and then within a year or so he left that completely and revolutionized the theory of integral equations. It's always change and always something new, and there's hardly anybody who is so flexible and so varied in his approach that Hilbert was.
His work is still talked about today, and his name has become attached to many mathematical terms. Mathematicians still use the Hilbert space, the Hilbert classification, the Hilbert inequality, and several Hilbert theorems. But it was his early work on equations that marked him out as a mathematician thinking in new ways. Hilbert showed that although there are infinitely many equations, there are ways to divide them up so that they are built out of just a finite set, like a set of building blocks. The most striking element of Hilbert's proof was that he couldn't actually construct this finite set. He just proved it must exist.
Somebody criticised this as theology and not mathematics, but really they'd missed the point. What Hilbert was doing here was creating a new style of mathematics, a more abstract approach to the subject. You could still prove something existed, even though you couldn't construct it explicitly.
It's like saying, I know there has to be a way to get from Göttingen to St. Petersburg, even though I can't tell you how to actually get there. As well as challenging mathematical orthodoxies, Hilbert was also happy to knock the formal hierarchies that existed in the university system in Germany at the time. Other professors were quite shocked to see Hilbert out bicycling and drinking with his students.
He liked very much parties.
Yeah?
Yes.
Party animal.
Yes.
Well, that's my kind of mathematician.
He loved very much dancing with young women. He liked very much to flirt.
Really? Most mathematicians I know are not the biggest of flirts.
Yet this lifestyle went hand in hand with an absolute commitment to maths.
Hilbert was, of course, somebody who thought that everybody who has a mathematical skill, a penguin, a woman, a man, or black, white, or yellow, it doesn't matter. He should do mathematics, and he should be admired.
The mathematics speaks for itself in a way.
The
it doesn't matter.
It doesn't matter which
when you're a penguin.
Yes, if you are a penguin, it's also.
If you can prove the Riemann hypothesis, we really don't mind whether you're a penguin.
Mathematics was for Hilbert a universal language.
Yeah.
Hilbert believed that this language was powerful enough to unlock all the truths of mathematics, a belief he expounded in a radio interview he gave on the future of maths on the 8th of September 1930.
Für uns gibt es kein Ignorabimus.
In it, he had no doubt that all his 23 problems would soon be solved, and that mathematics would finally be put on unshakable logical foundations.
There are absolutely no unsolvable problems, he declared, a belief that's been held by mathematicians since the time of the ancient Greeks. He ended with his clarion call: we must know, we will know.
Wir müssen wissen, wir werden wissen.
Unfortunately for him, the very day before, in a scientific lecture that was not considered worthy of broadcast, another mathematician would shatter Hilbert's dream and put uncertainty at the heart of mathematics. The man responsible for destroying Hilbert's belief was an Austrian mathematician, Kurt Gödel. And it all started here, Vienna. Even his admirers, and there are a great many, admit that Kurt Gödel was a little odd.
As a child, he was bright, sickly, and very strange. He couldn't stop asking questions, so much so that his family called him Herr Warum, Mr. Why.
Gödel lived in Vienna in the 1920s and 1930s, between the fall of the Austro-Hungarian Empire and its annexation by the Nazis. It was a strange, chaotic and exciting time to be in the city. Gödel studied mathematics at Vienna University, but he spent most of his time in the cafes, the internet chat rooms of their time, where amongst games of backgammon and billiards, the real intellectual excitement was taking place. particularly amongst a highly influential group of philosophers and scientists called the Vienna Circle. In their discussions, Kurt Gödel would come up with an idea that would revolutionise mathematics. He'd set himself a difficult mathematical test. He wanted to solve Hilbert's second problem and find a logical foundation for all mathematics. But what he came up with surprised even him. All his efforts in mathematical logic not only couldn't provide the guarantee Hilbert wanted, instead, he proved the opposite.
Got it. It's called the incompleteness theorem. Gödel proved that within any logical system for mathematics, there will be statements about numbers which are true, but which you cannot prove.
He starts with the statement, "This statement cannot be proved." This is not a mathematical statement yet, but by using a clever code based on prime numbers, Gödel could change this statement into a pure statement of arithmetic. Now, such statements must either be true or false. Hold on to your logical hats as we explore the possibilities. If the statement is false, that means the statement could be proved, which means it would be true, and that's a contradiction. So that means the statement must be true. In other words, here is a mathematical statement that is true, but can't be proved.
Mars.
Gödel's proof led to a crisis in mathematics. What if the problem you're working on, the Goldbach conjecture, say, or the Riemann hypothesis, would turn out to be true but unprovable? It led to a crisis for Gödel too. In the autumn of 1934, he suffered the first of what became a series of breakdowns and spent time in a sanatorium. He was saved by the love of a good woman. Adele Nimbersky was a dancer in a local nightclub. She kept Gödel alive. One day, she and Gödel were walking down these very steps. Suddenly, he was attacked by Nazi thugs. Gödel himself wasn't Jewish, but many of his friends in the Vienna Circle were. Adele came to his rescue. But it was only a temporary reprieve for Gödel, and for maths. All across Austria and Germany, mathematics was about to die. In the new German Empire in the late 1930s, there weren't colourful balloons flying over the universities, but swastikas. The Nazis passed a law allowing the removal of any civil servant who wasn't Aryan. Academics were civil servants in Germany then and now. Mathematicians suffered more than most. 144 in Germany would lose their jobs. 14 were driven to suicide or died in concentration camps. But one brilliant mathematician stayed on. David Hilbert helped arrange for some of his brightest students to flee, and he spoke out for a while about the dismissal of his Jewish colleagues. But soon, he too became silent.
It's not clear why he didn't flee himself, or at least protest a little bit more. He did fall ill towards the end of his life, so maybe he just didn't have the energy. All around him, mathematicians and scientists were fleeing the Nazi regime, until it was only Hilbert left to witness the destruction of one of the greatest mathematical centres of all time.
David Hilbert died in 1943. Only 10 people attended the funeral of the most famous mathematician of his time. The dominance of Europe, the centre for world maths for 500 years, was over. It was time for the mathematical baton to be handed to the new world. Time, in fact, for this place. The Institute for Advanced Study had been set up in Princeton in 1930. The idea was to reproduce the collegiate atmosphere of the old European universities in rural New Jersey. But to do this, it needed to attract the very best, and it didn't need to look far. Many of the brightest European mathematicians were fleeing the Nazis for America. People like Hermann Weyl, whose research would have major significance for theoretical physics. And John von Neumann, who developed game theory and was one of the pioneers of computer science. the Institute quickly became the perfect place to create another Göttingen in the woods. One mathematician in particular made the place a home from home.
Every morning, Kurt Gödel, dressed in a white linen suit and wearing a fedora, would walk from his home along Mercer Street to the Institute. On his way, he would stop here at number 112 to pick up his closest friend, another European exile, Albert Einstein.
But not even relaxed, affluent Princeton could help Gödel finally escape his demons. Einstein was always full of laughter. He described Princeton as a banishment to paradise. But the much younger Gödel became increasingly solemn and pessimistic.
Slowly, this pessimism turned into paranoia. He spent less and less time with his fellow mathematicians in Princeton. Instead, he preferred to come here, to the beach next to the ocean, walk alone, thinking about the works of the great German mathematician, Leibniz.
But as Gödel was withdrawing into his own interior world, his influence on American mathematics, paradoxically, was growing stronger and stronger. And a young mathematician from just along the New Jersey coast eagerly took on some of the challenges he posed.
2, 3, 4, 5, 6, 7, 8, 9, 10 times a day I could love you.
In 1950s America, the majority of youngsters weren't preoccupied with mathematics. Most went for a more relaxed, hedonistic lifestyle in this newly affluent land of ice cream and donuts. But one teenager didn't indulge in the normal pursuits of American adolescence, but chose instead to grapple with some of the major problems in mathematics. From a very early age, Paul Cohen was winning mathematical competitions and prizes. But he found it difficult at first to discover a field in mathematics where he could really make his mark. Until he read about Cantor's continuum hypothesis. That's the one problem, as I'd learned back in Halle, that Cantor just couldn't resolve. It asks whether there is or isn't an infinite set of numbers bigger than the set of all whole numbers, but smaller than the set of all decimals. It sounds straightforward, but it had foiled all attempts to solve it since Hilbert made it his first problem way back in 1900. With the arrogance of youth, the 22-year-old Paul Cohen decided that he could do it.
Cohen came back a year later with the extraordinary discovery that both answers could be true. There was one mathematics where the continuum hypothesis could be assumed to be true.
There wasn't a set between the whole numbers and the infinite decimals.
But there was an equally consistent mathematics where the continuum hypothesis could be assumed to be false.
Here, there was a set between the whole numbers and the infinite decimals. It was an incredibly daring solution. Cohen's proof seemed true, but his method was so new that nobody was absolutely sure. There was only one person whose opinion everybody trusted.
There was a lot of skepticism, and he had to come and make a trip here to the Institute right here to visit Gödel, and it was only after Gödel gave his stamp of approval in quite an unusual way by said, "Give me your paper," and then on Monday he put it back in the box saying, "Yes, it's correct." Then, of course, everything changed.
Today, mathematicians insert a statement that says whether the result depends on the continuum hypothesis. We've built up two different mathematical worlds, in which one answer is yes, and the other is no. Paul Cohen really has rocked the mathematical universe. It gave him fame, riches, and prizes galore.
He didn't publish much after his early success in the 60s. But he was absolutely dynamite. I can't imagine anyone better to learn from. And he was very eager to learn, to teach you anything he knew, or even things he didn't know.
With the confidence that came from solving Hilbert's first problem, Cohen settled down in the mid-1960s to have a go at the most important Hilbert problem of them all, the eighth, the Riemann hypothesis. When he died in California in 2007, 40 years later, he was still trying. But like many famous mathematicians before him, Riemann had defeated even him. But his approach has inspired others to make progress towards a proof, including one of his most famous students, Peter Sarnak.
I think overall, absolutely, I love the guy. It was my inspiration. I'm really glad I worked with him. He put me on the right track.
Paul Cohen is a good example of the success of the great American dream. Second-generation Jewish immigrant becomes top American professor. But I wouldn't say that his mathematics was a particularly American product. Cohen was so fired up by this problem that he probably would have cracked it whatever the surroundings.
Paul Cohen had it relatively easy. But another great American mathematician of the 1960s faced a much tougher struggle to make an impact. Not least because she was female. In the story of maths, nearly all the truly great mathematicians have been men. But there have been a few exceptions. There was the Russian Sofia Kovalevskaya, who became the first female professor of mathematics in Stockholm in 1889 and won a very prestigious French mathematical prize. And then Emmy Noether, a talented algebraist who fled from the Nazis to America, but then died before she fully realised her potential. And then there is the woman who I'm crossing America to find out about, Julia Robinson, the first woman ever to be elected president of the American Mathematical Society. She was born in St. Louis in 1919, but her mother died when she was 2. She and her sister Constance moved to live with their grandmother in a small community in the desert near Phoenix, Arizona.
Julia Robinson grew up somewhere around here. I've got a photo which shows her cottage in the 1930s with nothing much around it. And the mountains pretty much match those over there, so I think she might have lived just down there.
Julia grew up a shy, sickly girl, who when she was 7 spent a year in bed because of scarlet fever. Her ill health persisted throughout her childhood. She was told she wouldn't live past 40. But right from the start, she had an innate mathematical ability. Under the shade of the native Arizona cactus, she whiled away the time playing with endless counting games with stone pebbles. This early searching for patterns will give her a feel and love of numbers which would last for the rest of her life. But despite showing an early brilliance, she had to continually fight at school and college simply to be allowed to keep doing mathematics. As a teenager, she was the only girl in the maths class, but had very little encouragement. So the young Julia sought intellectual stimulation elsewhere.
Julia loved listening to a radio show called The University Explorer, and the 53rd episode was all about mathematics. The broadcaster described how he discovered that despite their esoteric language and their seclusive nature, mathematicians are the most interesting and inspiring creatures. For the first time, Julia had found out that there were mathematicians, not just mathematics teachers, that there was a world of mathematics out there, and she wanted to be part of it.
The doors to that world would open here at the University of California at Berkeley near San Francisco.
She was absolutely obsessed that she wanted to go to Berkeley, or not to Berkeley, she wanted to go away, someplace where there were mathematicians.
Right.
Berkeley certainly had mathematicians, including a number theorist called Raphael Robinson. In their frequent walks around the campus, they found that they had more than just a passion for mathematics. They married in 1952. Julia got her PhD and settled down to what would turn out to be her lifetime's work, Hilbert's 10th problem.
She thought about it all the time. She said to me she just wouldn't want to die without knowing that answer, and it had become an obsession.
Julia's obsession has been shared with many other mathematicians since Hilbert had first posed it back in 1900. His 10th problem asked if there was some universal method that could tell whether any equation had whole number solutions or not. Nobody had been able to solve it. In fact, the growing belief was that no such universal method was possible. How on earth could you prove that however ingenious you were, you'd never come up with a method? This argued that to show that no such method existed, all you had to do was to cook up one equation whose solutions were a very specific set of numbers. The set of numbers needed to grow exponentially, like taking powers of 2, yet still be captured by the equations at the heart of Hilbert's problem. Try as she might, Robinson just couldn't find this set. For the 10th problem to be finally solved, there needed to be some fresh inspiration. And that came from 5,000 miles away, St. Petersburg in Russia. Ever since the great Leonhard Euler set up shop here in the 18th century, the city has been famous for its mathematics and mathematicians. Here in the Steklov Institute, some of the world's brightest mathematicians have set out their theorems and conjectures. This morning, one of them is giving a rare seminar. It's tough going, even if you speak Russian, which unfortunately I don't. But we get a break in the middle to recover before the final hour.
There's a kind of rule in seminars that the first third is for everyone, the second third is for the experts, and the last third is just for the lecturer. So I think that's what we're going to get next.
The lecturer is Yuri Matyasevich, and he's explaining his latest work on, what else? The Riemann hypothesis. As a bright young graduate student in 1965, Yuri's tutor suggested he have a go at another Hilbert problem, the one that had in fact preoccupied Julia Robinson, Hilbert's 10th. It was the height of the Cold War. Perhaps Matyasevich could succeed for Russia, where Julia and her fellow American mathematicians had failed.
At first I did not like the approach.
All right.
The statement looked to me rather strange, artificial, but after some time I understood that it is quite natural, and then I understood that she had a new brilliant idea, and I just started to further develop in it.
And in January 1970, he found the vital last piece in the jigsaw. He saw how to capture the famous Fibonacci sequence of numbers, using the equations that were at the heart of Hilbert's problem. Building on the work of Julia and her colleagues, he'd solved the 10th. He was just 22 years old. The first person he wanted to tell was the woman he owed so much to.
And I got no answer. And I believed they were lost in the mail. It was quite natural because it was Soviet time.
But back in California, Julia had heard rumours through the mathematical grapevine that the problem had been solved. And she contacted Yuri herself.
She said, I just had to wait for you to grow up to get the answer, because she had started work in 1948.
When Yuri was just a baby.
And then he responds by thanking her and saying that the credit is as much hers as it is his.
I met Julia 1 year later. It was in Bucharest, and I suggested that after the Congress in Bucharest, Julia and her husband Raphael came to see me here in Leningrad.
Together, Julia and Yuri worked on several other mathematical problems, until shortly before Julia died in 1985. She was just 55 years old.
She was able to find new ways. Many mathematicians just combined previously known methods to solve new problems, and she had really new ideas.
Although Julia Robinson showed that there was no universal method to solve all equations in whole numbers, mathematicians were still interested in finding methods to solve special classes of equations. It would be in France in the early 19th century, in one of the most extraordinary stories in the history of mathematics, that methods were developed to understand why certain equations could be solved while others couldn't. It's early morning in Paris on the 29th of May 1832. Everys Galois is about to fight for his very life. It's the reign of the reactionary Bourbon king Charles X. And Galois, like many angry young men in Paris then, is a republican revolutionary. Unlike the rest of his comrades though, he has another passion: mathematics. He'd just spent 4 months in jail. Then, in a mysterious saga of unrequited love, he's challenged to a duel. He'd been up the whole previous night, refining a new language for mathematics he'd developed. Galois believed that mathematics shouldn't be the study of number and shape, but the study of structure. Perhaps he was still preoccupied with his maths. There was only one shot fired that morning. Galois died the next day, just 20 years old. It was one of mathematics' greatest losses. Only by the beginning of the 20th century would Galois be fully appreciated and his ideas fully realized. Galois had discovered new techniques to be able to tell whether certain equations could have solutions or not. The symmetry of certain geometric objects seemed to be the key. His idea of using geometry to analyze equations will be picked up in the 1920s by another Parisian mathematician, André Weil.
I was very much interested and so far as school was concerned quite successful in all possible branches.
And he was. After studying in Germany as well as France, André settled down at this apartment in Paris, which he shared with his more famous sister, the writer Simone Weil. But when the Second World War broke out, he found himself in very different circumstances.
He dodged the draft by fleeing to Finland, where he was almost executed for being a Russian spy. On his return to France, he was put in prison in Rouen to await trial for desertion. At the trial, the judge gave him a choice: 5 more years in prison or serve in a combat unit. He chose to join the French army, a lucky choice, because just before the Germans invaded a few months later, all the prisoners were killed.
They only spent a few months in prison, but this time was crucial for his mathematics, because here he built on the ideas of Galois and first developed algebraic geometry, a whole new language for understanding solutions to equations. Galois had shown how new mathematical structures could be used to reveal the secrets behind equations. Weil's work led him to theorems that connected number theory, algebra, geometry and topology, and are one of the greatest achievements of modern mathematics. And without André Weil, we would never have heard of the strangest man in the history of maths, Nicolas Bourbaki. There are no photos of Bourbaki in existence, but we do know that he was born in this cafe in the Latin Quarter in 1934, when it was a proper cafe, the Café Coupelard, and not the fast food joint it's now become. Just down the road, I met up with Bourbaki expert David Orban.
I must say, actually, when I was a graduate student, I got quite frightened when I used to go into the library, because this guy Bourbaki had written so many books.
Something like 30 or 40 altogether. In analysis, in geometry, in topology, it was all new foundations.
Virtually everyone studying maths seriously anywhere in the world in the 1950s, 60s and 70s would have read Nicolas Bourbaki.
And he also applied for membership of the American Math Society, I heard. But
At which point he was denied membership.
Really?
On the ground that he didn't exist.
Oh.
The Americans were right. Nicolas Bourbaki does not exist at all, and never has. Bourbaki is in fact the nom de plume for a group of French mathematicians led by André Weil, who decided to write a coherent account of the mathematics of the 20th century. Most of the time, mathematicians like to have their own names on theorems. But for the Bourbaki group, the aims of the project overrode any desire for personal glory. After the Second World War, the Bourbaki baton was handed down to the next generation of French mathematicians. And their most brilliant member was Alexander Grothendieck. Here at the IHES in Paris, the French equivalent of Princeton's Institute for Advanced Study, Grothendieck held court at his famous seminars in the 1950s and 1960s.
He had this incredible charisma, and he had this amazing ability to see a young person and somehow know what kind of contribution this person can make to this incredible vision he had of how mathematics, so to speak, could be.
And this vision enabled him to get across some very difficult ideas indeed.
He says, suppose you want to open a walnut. So the standard thing is you take a nutcracker and you just break it open. And he says his approach is more like you take this walnut and you put it out in the snow and you leave it there for a few months. And then when you come back to it, it just opens.
Grothendieck is a structuralist. What he's interested in are the hidden structures underneath all mathematics. Only when you get down to the very basic architecture and think in very general terms will the patterns in mathematics become clear. Grothendieck produced a new powerful language to see structures in a new way. It was like living in a world of black and white and suddenly having the language to see the world in colour. And it's a language that mathematicians have been using ever since to solve problems in number theory, geometry, even fundamental physics. But in the late 1960s, Grothendieck decided to turn his back on mathematics after he discovered politics.
He believed that the threat of nuclear war and the questions of nuclear disarmament were more important than mathematics. And that people who continued to do mathematics rather than confront this threat of nuclear war were doing harm in the world.
Grothendieck decided to leave Paris and move back to the south of France where he grew up. Bursts of radical politics followed, and then a nervous breakdown. He moved to the Pyrenees and became a recluse. He's now lost all contact with his old friends and mathematical colleagues. Nevertheless, the legacy of his achievements means that Grothendieck stands alongside Cantor, Gödel and Hilbert as somebody who has transformed the mathematical landscape.
He changed the whole subject in a really fundamental way. I mean, it'll never go back. Certainly he's the dominant figure of the 20th century.
I've come back to England, though, thinking again about another seminal figure of the 20th century. The person that started it all off, David Hilbert.
Of the 23 problems that Hilbert set mathematicians in the year 1900, most of them now have been solved. However, there is one great exception, the Riemann hypothesis, the 8th on Hilbert's list. That one is still the holy grail of mathematics.
Hilbert's lecture inspired a generation to pursue their mathematical dreams. This morning, in the town where I grew up, I hope to inspire another generation.
Thank you. Well, hello, my name's Marcus de Sautoy, and I'm a professor of mathematics up the road at the University of Oxford. But it was actually in this school here, in fact, this classroom, is where I discovered my love for mathematics.
And this love of mathematics that I first acquired here in my old comprehensive school still drives me now. It's a love of solving problems. There are so many problems I could tell them about, but I've chosen my favourite.
I think that a mathematician is a pattern searcher, and that's really what mathematicians try and do. We try and understand sort of the patterns and the structure and the logic to explain the way the world around us works. And this is really at the heart of the Riemann hypothesis. The task is there any pattern in these numbers which can help me to say where the next number is going to be? What's the next one after 31? How can I tell?
These numbers are, of course, prime numbers, the building blocks of mathematics. The Riemann hypothesis, a conjecture about the distribution of the primes, goes to the very heart of our subject.
Why on earth is anybody interested in these primes? Why is the army interested in primes? Why are spies interested in primes?
Isn't it to encrypt stuff?
Exactly. I study this stuff because I think it's all really beautiful and elegant, but actually there's a lot of people who are interested in these numbers because they're very practical use.
The bizarre thing is that the more abstract and difficult mathematics becomes, the more it seems to have applications in the real world. Mathematics now pervades every aspect of our lives. Every time we switch on the television, plug in a computer, pay with a credit card, there's now $1 million for anybody who can solve the Riemann hypothesis. But there's more at stake than that.
Anybody who proves this theorem will be remembered forever. They'll be up on that board ahead of any of those other mathematicians.
And that's because the Riemann hypothesis is a cornerstone of maths. Thousands of theorems depend on it being true. Very few mathematicians think that it isn't true, but mathematics is about proof, and until we can prove it, there will still be doubt. Maths has grown out of this passion to get rid of doubt. This is what I've learned in my journey through the history of mathematics. Mathematicians like Archimedes and Al-Khwarizmi, Gauss and Grothendieck were driven to understand the precise way numbers and space work.
Maths in action, that one. It's beautiful. It's really nice, yeah.
Using the language of mathematics, they've told us stories that remain as true today as they were when they were first told. In the Mediterranean, I discovered the origins of geometry.
Mathematicians and philosophers flocked to Alexandria, driven by their thirst for knowledge and the pursuit of excellence.
In India, I learnt about another discovery that it'd be impossible to imagine modern life without.
So here we are, in one of the true holy sites of the mathematical world. Up here are some numbers, and here's the new number. It's 0.
In the Middle East, I was amazed at Al-Khwarizmi's invention of algebra.
He developed systematic ways to be able to analyse problems so that the solutions would work whatever the numbers that you took.
In the golden age of mathematics in Europe in the 18th and 19th centuries, I found how maths discovered new ways for analysing bodies in motion, and new geometries that helped us to understand the very strange shape of space.
It is with Riemann's work that we finally have the mathematical glasses to be able to explore such worlds of the mind.
And now my journey into the abstract world of 20th century mathematics has revealed that maths is the true language the universe is written in, the key to understanding the world around us. Mathematicians aren't motivated by money and material gain, or even by practical applications of their work. For us, it's the glory of solving one of the great unsolved problems that have outwitted previous generations of mathematicians.
Hilbert was right. It's the unsolved problems of mathematics which make it a living subject, which obsess each new generation of mathematicians. Despite all the things we've discovered over the last 7 millennia, there are still many things we don't understand. And it's Hilbert's call of we must know, we will know, which drives mathematics.
You can learn more about the story of maths with the Open University at open2.net.
How do you think our survey of mathematical history added up? Have your say on